Cool. All right. Cool. Hello, everyone. Good morning. Thanks a lot for getting up so early and joining this session here at the start, despite any jet lag that you might have. It's really great to see so many of you here in person today at this tutorial on modular and parameter efficient fine-tuning. And so for this tutorial, I'll be speaking in person here for the first part, and then I'll give it over later to Jonas, who's also at Google, and Ivan, who's at the University of Cambridge, and PolyAI. And in general, I think, yeah, I hope you can also hear me on Zoom, so that should be fine. Cool. So so you can see this tutorial basically in kind of the context of a development that we are probably all familiar with, which is that recent models in NLP have been getting larger and larger. So we can see from kind of the inception of these contextualized deep representations with Elmo and BERT to kind of orders of magnitude larger models like Palm recently, GPT-3, or the Turing models. And if this trend continues, we might reach like trillion parameter models very soon. So here just some logistics for this tutorial. Okay, this is fine. The slides are all available online via this short link that you can access if you want. If you have questions, you can ask them either on Zoom directly. In Rocket Chat, there's a separate tutorial channel. You can ask them either throughout the session or afterwards. We're going to check that throughout the conference. Or you can ask them just in the breaks or after the session as well. And if you don't like this kind of spoken presentation format, we're also at the moment kind of writing up a survey on kind of a broader look of this area that you can also read in text form, hopefully on the archive server near you. Cool. So having said that, I guess the main reason why these models have been growing larger and larger is that not only that with these increasing number of parameters, people have observed that as we scale up these models, both in their pre-trained data and parameter size, that these models are able to learn much more sophisticated natural language understanding capabilities in practice. And here, I think one kind of illustrative figure of kind of the perhaps the like GPT-3 era of transfer learning is kind of this general paradigm of having your pre-trained method. Before that, we used to pre-train word embeddings. More recently, methods like GPT-3 or BERT that were pre-trained on large amounts of unlabeled data. And then in the second step, fine-tuned on label data that were collected using kind of human annotators or by crowdsourced labelers in practice for a diversity of different tasks. And this is really what I think led to most improvements and most state-of-the-art performance in NLP, perhaps until very recently. However, now, kind of in light of this increasing size of models, just being able to fine-tune now these like 500 billion parameter models in practice is not really feasible anymore. We're not doing that anymore for like all of the tasks we actually care about. So in light of these huge model sizes, this kind of formula of just pre-training and fine-tuning model has really been breaking down more recently. And as a result, and I think what a lot of work, at least with regard to these large models, has shifted to is instead doing something that you're probably all familiar with. So you're doing this in context learning, where you write as a human or researcher, you write a prompt for a given task and perform kind of in-context updates using this model and this prompt. And this has kind of been, in fact, so kind of simple, but also quite successful or like surprisingly successful in practice that like from GPT-2 to GPT-3, that the number of these papers that use some sort of prompting or some sort of in-context learning has really kind of skyrocketed over kind of the last month or the last two years, I guess. However, this prompt-based learning doesn't come without its downsides. So in practice, the model, in order to be able to perform prediction, it needs to see this prompt that you've written for every example. And as we know that transformers kind of scale, or standard transformers scale quadratically with the input size. So the longer the prompt is and the more in context examples you include, the more expensive it is to actually process for every example. In practice, from early on, early results until recently as well, we've also seen that typically if you're able to fine tune, that will result in an increased performance, and prompting, just because you're only able to see a few examples, typically underperforms fine tuning on a larger amount of examples. There's also been kind of a large number of different studies that looked into all the kind of different ways that prompts can fail, from the way the prompt is formulated to the examples that you feed into the prompt, to how these examples are ordered. So there's a lot of kind of different knobs that you have to turn in order to actually maximize the potential of this sort of prompt-based learning. And finally, even though we've been, or people in the community have been using prompting for the last 3 years, we still do not really understand what the model actually learns from the prompt, or how a good prompt is actually, what are the ingredients in a good prompt. And in fact, recently a paper at this conference, for instance, showed that even random labels in a prompt can lead to good performance. So it's really kind of still quite unclear of what the model actually extracts from these short task-based descriptions. So in light of this, and this is kind of where this talk here comes in, where we're going to be talking about an alternative paradigm to prompting that is particularly useful for adapting these large-scale models, which instead of fine-tuning all of the model parameters, we are essentially going to do parameter-efficient fine-tuning. And how this looks like in practice, where you can see kind of the full fine-tuning on the left here, where we would typically update all of the model parameters for a given task. Now, in this sort of parameter-efficient fine-tuning regime, we're only going to be updating a subset of the model parameters. And if you kind of look at this figure, you might ask yourself, okay, isn't this something that we've used to do, or we've done before? For instance, in computer vision, when kind of transfer learning or ImageNet-based transfer learning started there, it was very common just to update the last layer only of these ImageNet pre-trained models. Also in NLP, very early on, people experimented with using both static, so non-fine-tuned, and fine-tuned word embeddings, and even Elmo kind of in the original paper basically just use these contextualized representations as features, so without actually fine-tuning them. And kind of in all of these regards, we've actually found that fine-tuning all representations actually worked better in practice. So in all cases, people have kind of shifted towards fine-tuning all of the model parameters, really. So the question for this tutorial is really, okay, why does it make sense now, given these huge models, to go back to fine-tuning just a small set of parameters? And I think there's kind of 3 main reasons for that. The first one is that, as I mentioned already before, fine-tuning all parameters with these models is simply typically impractical in practice. Secondly, in this kind of regime of huge models and of over-parameterized models in particular, we've kind of observed something that was not really evident, or was not really possible with smaller models, which is that because these models are so huge and so over-parameterized, we actually can get away with and can match model performance by just updating a small set of parameters. And that's been something that's been shown kind of across different methods in practice. And the last point, and that's where kind of the other part of the tutorial title comes in, is that only updating a small subset or a small number of parameters gives rise to representations that are modular and compositional. So what do we mean by modularity and compositionality here? So in general, you can kind of see that in this context here as the ability of having learned representations for a certain task or skill, and having some other modular representations for another setting or another task, and being able to recombine and compose these representations to perform some new combination of tasks that you previously weren't able to, or that you haven't observed during training. So in practice, modularity can have a number of benefits. In particular, as I already mentioned, given that these models have really been increasing in size, it can allow us to perform these parameter-efficient fine-tuning strategies. It can also allow us to generalize to scenarios that we haven't seen during training. So if we have a skill, or if we have seen some data in English and some data in Swahili, and where we only have seen the task in English, we might be able to learn or perform the same task in Swahili without ever having seen task data in the corresponding language. So these modularity can lead to out of distribution generalization to some extent. Thirdly, they can also help us dealing with something that we've kind of seen when trying to adapt these models in a continual setting, which is kind of catastrophic or negative interference between different fine-tuning settings or different tasks. So in practice, and with these large models, it's particularly relevant if we want to train models across different settings or different modalities, for instance, where if we want to train kind of the same model on all of these different data sources, these can cause kind of negative transfer or some deterioration in performance for the different settings. And here, kind of designing the model to be modular from the start can help us kind of disentangle these different data sources. And finally, kind of as we come to kind of designing models that we want to keep continuously updated and continuously up to date over time, modularity can also help us keeping information consistent and up to date. So for instance, if we really exactly know where certain information like who is the president of the US, where that is located in the model, it's going to be very easy to update only those sets of parameters that pertain to that information in order to then represent new information as that becomes available. So you can also see this tutorial kind of in the context of some like recent and relevant tutorials here in the ACL community. So kind of the most relevant recent ones were a tutorial at EMNLP 2020 on high performance NLP. And in that tutorial, they focused more on kind of efficient methods. So how you can make your model efficient and at inference time via knowledge distillation, quantization, or pruning. Pruning is also something that we're going to talk about here, but more in the context of how we can get sparse representations in our models. And the other relevant tutorial here is at ACL this year, which focused more on how we can get the most out of limited or very few samples. And they in particular, so if you want to learn more about prompting or in context learning or kind of some other forms of like meta learning, the slides for that tutorial are also available online. So now, before we get to kind of the main meat and the main content of the tutorial, here just kind of a brief disclaimer of the main goal. So we are mainly going to aim to provide an overview of these kind of family of parameter-efficient fine-tuning methods. And in particular, we also want to highlight kind of the benefits and the use cases for modular representations, because we really believe that this is kind of a good alternative way compared to in-context learning. We try to cover kind of as many papers or really representative papers of these different methods, but given that there's kind of been an increasing recent interest in this area, it hasn't really been possible to cover comprehensively everything. So if you've maybe worked yourself on this area and we've missed something, feel free to reach out. But yeah, just kind of keep in mind that there's only kind of a representative subsection of papers. And in particular, what we're not covering here, so we're not going too deep into prompting methods and only mainly cast them as kind of one example of these parameter efficient methods. And we are also not going to talk too much about just generally efficient NLP, but mostly look at efficiency kind of through the lens of how we can use it to adapt these pre-trained models. But if you're more interested in these particular areas, there are two relevant surveys here that are quite recent, so they're quite up to date with current literature that you can check out. And if you look at the slides, all of the links on the slides are also directly hyperlinked, so you can just click on the link and it will get you to the paper directly. So having said that, here's kind of a rough agenda, and you can see this agenda kind of roughly in the context of like a general architecture of parameter efficient models. So here on the left, you can kind of see a general architecture in like a standard like transformer layer, where you can see kind of roughly, if you're familiar with that, the query, key, and value matrices, kind of Q, K, key, and B here, and then the feed-forward layer at the top. And in the middle, we have these like modular components, which we're going to talk about in depth. So there's only kind of a schematic representation and no need to fully understand all of that. But the main components that we're going to talk about in this tutorial are essentially these kind of components in pink here, which are kind of the main modular representations that we seek to learn. In addition, and these are what we're going to cover in the main first section of the talk. In the second part, we're going to focus more on how we can actually use and combine these representations. So most modular models have a second component that is known as routing, that basically decides when and in what circumstances we want to use which modular representation. And then secondly, having learned these modular representations, there can also be typically an aggregation component that decides how we can combine or aggregate the representations that we've learned. And finally, in the last part of the tutorial, we're going to talk about applications. So in what kind of settings these models have actually been used in NLP. And we are particularly looking at kind of NLP methods and with regard to multilinguality and kind of multi-domain settings. All right, so let's get started on the first part of the talk here. And so I'm just in the beginning, I'm just going to dump a bit of notation on you. This is just all on the same slide, but hopefully should not be like too complicated. So it's just to get us kind of all on the same page regarding the rough formulation that we're going to use here. And the main thing that you can see here is, so we are just generally going to talk about neural networks. In this case, we're going to define a neural network basically just as a function f here. That is parameterized by some parameters theta, and the function just maps from an input space here to a label output space. And we're going to view this this kind of general neural network as composed of different functions. So all of these can be like smaller subfunctions that can be either layers or smaller parts of the layer, like a feed-forward network. And each of the layers also is parameterized by its kind of separate parameters that we just kind of index here as an index of the overall parameters. So this is kind of the pre-trained model, the base neural network that we're going to be using. And then on the kind of modularity side, we're going to talk about these kind of modular representations in terms of having parameters phi here. And each modular representation is going to be associated with a kind of with a subfunction here that again is just f here. And throughout the tutorial, we're basically going to talk about kind of three, we're going to characterize these parameter efficient representations into three different subcategories. The first one we're going to call here as parameter composition. So this is essentially the setting where we have a function f, where we have already some existing parameters theta, and we're just going to combine our existing parameters with these new modular parameters phi, kind of on the parameter level, by interpolating them on the level of individual weights, by either adding them element-wise or multiplying them. Secondly, we're going to talk about input composition. And in this case, this just means that we concatenate here our modular parameters phi with the input. So this is, for instance, something that you can see with prompting, where you have your prompt and you concatenate that with the remaining input of the model. And finally, in this kind of the most general category, function composition, where we have our existing function of the model f theta here. And then we're going to compose that in some way with kind of an arbitrary new function that we've learned, which can be, which is again parameterized by these phi parameters. And kind of the main reason or why we are going to be talking about these modular parameters is because in practice, when we fine-tune the model, we keep all of the parameters theta here of the main model typically fixed, and only update the parameters phi here of these modular representations. So these are kind of treated as separate and separately updated from the remaining parameters of the model. Cool. So from this mathematical formulation, here's just for these three different categories a kind of more schematic representation that should hopefully make it a bit clearer how these kind of differ. And in particular, you can see here, so all of these are basically kind of seen in the context of a transformer layer, where again, we have here our multi-head attention block with the query key and value matrices, and then the feed-forward layer at the top. And we can basically see here that for the parameter composition, this is basically can be applied to different weight matrices. And here we basically just learn particular individual weights for as modular representations. For input composition, we can combine what we feed here. So in addition, so the input here is kind of fed into these key value and query matrices. And in practice, we can kind of just concatenate some other modular parameters in front of that. And finally, for function composition, we can kind of insert a completely new function, in this case, just a bottleneck layer into our existing model. Cool. So parameter composition, again, we can, is probably kind of one of the most largest and most diverse categories. And we can, again, subcategorize that into three separate ones. In particular, kind of sparse networks, structured kind of methods, and methods that use low rank representations. So with regards to sparse networks, I think this is something that probably all of you have are aware of or have heard of already. And in general, kind of main motivation here is that it can be a useful inductive bias to kind of enforce these modular parameters to be sparse. So just to only act or only modify a certain subset or a certain sparse subset of all of the parameters of the model that are most important. The kind of most common way that we can induce sparsity is via pruning. And pruning can be done in different ways, or can be seen in different perspectives. But the kind of one way that you can view pruning is by essentially applying a binary mask for the model, kind of on the level of the individual weights here, that for each weight basically decides whether to keep that, whether to keep it at its weight parameter value, or whether to remove it, so to set it to 0. And as a result of applying this binary mask to the model, we essentially get a sparse network as a result. And the most common way that we can kind of induce the sparsity or to decide which of these connections we want to set to 0 is by looking at simply the kind of overall magnitude of the weight. And so in practice, pruning basically kind of looks like this, in that we have a model, initially trained model, often that started from a randomly initialized model, but in this context, it's typically a pre-trained model. Then we, after having this pre-trained model, we basically just sort all of the weights based on the magnitude and then prune, so remove a certain subset or a certain proportion of the lowest magnitude weights, which will then give us kind of a rise to a pruned model, which has kind of a smaller number of connections here. In practice, what is typically done and what typically performs better rather than just trying to remove all of the weights at the same time is to do multiple iterations of this pruning. So if we just do one iteration of pruning, this is typically known as one-shot pruning. So typically what people are doing is iterative pruning or iterative magnitude pruning by essentially doing one pruning iteration and then repeating that a couple of times until you've reached your desired sparsity kind of threshold. And this is something that has been kind of most common in this in the lottery ticket hypothesis, for instance. Now, kind of for our purposes, we can also view pruning basically through the lens of as the addition or modification of the existing parameters of the model. And specifically, we can basically view the, because typically, as we've kind of seen here, we would always kind of retrain the non-pruned components. So we can basically view pruning as basically adding this like sparse parameter vector phi here to the existing parameters of the model, where the parameter phi basically has values where our binary mask is not 0. And in practice, kind of the typical way that people do pruning, as I mentioned, is by actually setting parameters or setting values to 0. So you can basically, if you are just using kind of this formulation here, you would only kind of add your updates or add the subnetworks for the sparse set of parameters, but would still keep the other parameters fixed. And in this case, if you multiply the parameters, the existing parameters with the binary mask before, you would basically set only the pruned parameters or the parameters that you're going to prune to 0 and only have a sparse network as a result. And here there's just the kind of element-wise multiplication, basically. And in practice, kind of in the typical pruning literature, people are typically setting these parameters to 0, and which they've kind of shown to perform a bit better for randomly initialized models. And kind of the main hypothesis or the main explanation is that most of the parameters that you're going to set to 0 are parameters that would have kind of tended to 0 anyway. So pruning here can be kind of seen as a form of learning to some extent. But as we'll see later, in kind of using pre-trained models, is actually kind of this formulation has been a bit more common in actually keeping the pre-trained values the same, and then just adding this sparse parameter value to the pre-trained parameters. So in the context of pruning and kind of to understand a bit the dynamics of these subnetworks, it's kind of important or useful to talk kind of about a recent observation or insight in this area, which has been come to known as the lottery ticket hypothesis. And that goes back to a paper from NeurIPS 2019, which basically observed that if you look at kind of dense, randomly initialized and initially quite small models, they've observed that these kind of randomly initialized models contain subnetworks, so sparse subnetworks, that if you only train these subnetworks in isolation, they can reach the same test accuracy, in that case in some computer vision tasks, as if you would train kind of the full model doing kind of regular fine-tuning. And this kind of hypothesis or this observation has since been validated for other settings. So this has been both applied in reinforcement learning as well as in NLP as well, and for larger models in computer vision. And recently, people have also naturally kind of looked at whether the same holds for kind of pre-trained models like BERT. And people have indeed found that if you look at kind of BERT pre-trained representations and you kind of use the same pruning method that I specified before of doing iterative magnitude pruning on them, and only then train the subnetworks in isolation, that you indeed get subnetworks that can essentially almost match the regular fine-tuning accuracy. And people have observed that kind of the sparsity ratio for these networks is task dependent. So for some more complex tasks, you want to keep more connections in your model, whereas for maybe simpler tasks, you can prune almost all of the parameters of your pre-trained model. In practice, these studies have also observed that actually the pre-trained initialization is quite important. So if you would do the same thing for a random, instead with a random initialized model, this would be a lot worse. Actually, having just this pre-trained starting point from BERT is quite useful, even for random subnetworks, which kind of makes sense given what we've all, I think, learned about transfer learning in practice. And then one study also showed that even if you just do kind of random pruning, so if you take your pre-trained representations and even just select random subnetworks in them, these can also perform surprisingly well. And kind of the last observation here is that subnetworks trained on a general task, like masked language modeling, also transfer better. So the structure of these subnetworks also transfers better to other tasks, because the training task is quite representative. And kind of lastly, if you kind of select the correct sparsity ratio for a given task, where there's kind of a like a phase shift essentially, one study has also shown that there can be what they call super tickets, which can even kind of outperform your underlying full fine-tuned model if you really kind of tune the parameters right. So kind of moving beyond lottery tickets, here, like so far, we've basically talked about just pruning the model and then kind of retraining the subnetwork, which can allow us to achieve good performance. But if we have a very huge model, the number of possible subnetworks actually is, kind of grows almost infinite or combinatorially with the number of parameters of the model. So in practice, given kind of this huge amount of combinations of possible subnetworks in the model, it's actually maybe not that surprising, but still very, very interesting that there are certain kind of mask combinations, what they call supermasks here, that if without actually pre-training, so without retraining just these subnetworks, actually allow you to achieve kind of non-random performance for different tasks. And in this case, they've basically shown that for kind of some simple computer vision tasks like MNIST, and kind of more smaller models, that even for these kind of smaller tasks and for randomly initialized models, only selecting the subnetwork here without any actual retraining actually leads to non-random performance here. So in this case, basically, we just have a model that we would initially train to basically select the pruning or the subnetwork, but then again, like after that, just set the prune subnetwork back to its original initial random parameterization. And in this case, kind of in our formulation, this kind of setting, if you only basically learn the mask, can basically just be represented as like learning just these 5 parameters, in this case, just this binary mask, and applying this directly to our existing model. And this is also something, so just kind of learning this mask instead of actually adding any additional task-specific parameters, is also something that, in practice, kind of can allow you to accommodate a potentially unlimited number of potential masks kind of in the underlying model. So if you just have, if the only task-specific component is the mask that you've learned, you can essentially have kind of one supermask that you've learned here for task A, and different other supermasks for other tasks that for each task only require a very small number of parameters for their specification. Now these supermasks have also been kind of under a different name, also been used in models like BERT, where kind of the strategy of just masking, so not updating the subnetworks, but only learning how you should mask your model, has also been found useful with a pre-trained model like BERT. And in this case, the way they learned the mask is kind of similar to prior work in computer vision, where they effectively learned a real valued mask first, and then basically just defined a threshold function. So basically kind of learned a function here that, given this kind of real valued mask and a thresholding parameter tau here, basically just binarizes that. And then with this binarized mask in hand, we essentially get the final mask that we can use to get our sparse subnetwork in the end. And just kind of one point here in terms of how this kind of binary mask can actually be learned. And this is something where that kind of people have in the past basically used this straight-through estimator, which essentially just kind of estimates the gradients straight through by just effectively ignoring the thresholding function and using the gradients of this binary mask here as essentially an estimate of the gradients of the real mask parameters. And kind of one observation here, or one thing that is kind of practically useful for NLP models, is that so you can apply this masking to like all of the parameters of the model. But in practice, one kind of part of the model that they've identified that you don't want to mask is the embedding layer, because in the embedding layer, kind of the subnetworks of the combinations are generally still useful for all tasks. So that's something that you do not want to mask. But beyond that, kind of masking, kind of similar to other studies, they found also mostly useful in the kind of upper layers of the model. So With that in mind, so the kind of approaches that I've talked before were kind of more focused on like standard pruning. So pruning as it has been previously applied to randomly initialized models. So models that were just trained on a random initialization and that do not really take account that the initial configuration, the initial initialization that we have for our pre-trained models is already quite informative. So for better pruning these pre-trained models, this is also something that we should consider. So how our pre-trained or how the fine-tuned parameters actually differ or change from our pre-trained initialization. And in this context, so the magnitude pruning that we've seen before, basically, as I mentioned, just looks at the magnitude of the model. So how far the final fine-tuned parameters are in the end from zero. Which doesn't really take into account kind of the original starting point from the pre-trained initialization. So in this context, kind of an alternative pruning technique has been proposed, which was named movement pruning. So instead of basically looking at the overall magnitude, we basically only look at kind of the magnitude of the change in doing fine-tuning. So how far the parameters doing fine-tuning have actually moved away from zero. And in this case, we can basically look at kind of this figure here, where here we basically see the parameters. So we have both a plot showing which parameters were tuned using kind of regular magnitude pruning. And then here we see the same plot for movement pruning. And the gray values in both cases are essentially the prune parameters, and the kind of orange and yellow parts respectively are the parameters that we keep. And we can see here that, yeah, and we have on the axis basically kind of the values at the pre-trained initialization and then where they end up doing fine-tuning. And we can see basically that doing magnitude pruning, we basically kind of pruning the parameters irrespectively of where they kind of started out doing pre-training, just only based on kind of this range of being around zero after fine-tuning. And in contrast, doing fine-tuning, we basically only prune the parameters here that kind of started out further away from zero before, and then moved closer to zero, so moved closer to the middle and kind of to the bottom, so closer to the middle of the plot doing fine-tuning, which allows us to be kind of more selective and kind of more task-specific into regarding how we actually select the parameters. So where magnitude pruning basically selects the same parameters or like, yeah, is typically kind of does not really consider the task much in practice, because most parameters stay very close to their pre-trained initialization. Movement pruning is much more sensitive, or allows us to much more incorporate the particular parameters that will be salient or most important for particular downstream task. In this context, there's also kind of been an alternative method applied for fine-tuning, which is called diff pruning, where they basically also kind of use this formulation of having your initial parameters and basically learning this additional parameter vector phi here, which is sparse, and added to the existing parameters. And in this case, they basically just prune this parameter vector phi here to make it sparse. So this is basically very similar to, or similar in some sense to movement pruning, where now instead of looking at the kind of overall magnitude of the parameters that are plus phi, we are only pruning based on the magnitude of the parameters phi here, which results again kind of in a sparse update and in a kind of modular set of parameters. And yeah, so this is basically kind of just as a more fine-tuning specific way of magnitude pruning, now only apply to these phi parameters. I mentioned before that typically in most kind of standards or classic work on pruning, typically people are setting the parameters to a random initialization, and some recent work on fine-tuning pre-trained models actually kept the parameters the same and just added the additional task-specific parameter on top of it. So in practice, as I mentioned, for at least for randomly initialized models, people have observed that actually setting them to zero can be useful in practice, and in the end kind of results in a sparse model like overall. However, if you zero all of the original parameters of the model, that actually does not allow you to fully kind of make use of some of the modular properties of these models in practice. So kind of one here with the next method, I want to quickly illustrate some of these properties, and we're going to talk more about these in depth in the latter sections of the talk. And so one recent method basically also uses this formulation of applying magnitude pruning to this additional parameter vector phi here that we're learning. And what this allows us in practice is that for each task and for each setting, we effectively now just have a sparse vector phi that we can combine together. So in their case, and we're going to talk more about that in depth later on, they can basically learn sparse vector phi here, both for a particular language based on some self-supervised pre-trained task, as well as for a particular task, and then kind of recombine and compose simply through addition these separate parameter vectors phi here. And that's not something that would really be possible if you, in addition, kind of mask the original parameters of the underlying model as well. Cool. So this was basically kind of the largest kind of individual subsection of the talk. Now, kind of for the second subsection here, which focuses on kind of how we can introduce additional structure information about the model into the way we learn these modular parameters. And in particular here, kind of the main intuition is that if we kind of know how our model is structured, so which of the parameters are associated with particular weight matrices or different layers, this can also kind of inform the way we learn these modular parameters. So specifically, kind of in an abstract sense, we can essentially add kind of another setting, define a group G here, and we can only basically say that we only learn kind of modular parameters for functions that are in a certain predefined group G, whether that is parameters that are in a certain layer or in a certain set of parameters like your feed-forward attention weight matrix. So to look at this a bit more in depth about how this has been done kind of in general work. So these groups can relate to, so the main way or kind of one classic way that we can look at defining these groups is basically just looking at a particular layer and only updating kind of sparse parameters within this particular layer. But we can also kind of use a group to define a more fine-grained component in a model. For instance, kind of one common choice or one practical choice for using this group is by defining group to only consist of the bias parameters in our model. In practice, and this is something that has been kind of shown in computer vision here, if you actually look at kind of the way you compute your gradients into the model through backpropagation, if you only update the bias parameters of the model, you actually do not need to require, or you're not required to store the activations of your model in order to compute those gradients. So in practice, doing training, this can save you a lot of kind of peak memory by not having to store these for gradient computation. So here, this is basically kind of a just updating a general convolutional neural network where you can see here like the full fine-tuning, and you can basically see here with the fully colored in parts of the section, which parameters are kept in memory. So for standard fine-tuning, you basically need to keep all of the parameters, so both of the convolutions and all of the filter parameters, as well as the bias parameters here, all of them in memory to compute all of their gradients. But in this case, if you only update the biases, you do not need to store any of these and only need to store the bias parameters in memory. So this is something that kind of effectively can be quite memory efficient during training. And in NLP, kind of the same method has been proposed as well. In that case, it's been proposed under the name of bitfit, which effectively does kind of the same thing of only updating the bias parameters. And just to stress here, so in kind of in the previous part, we basically talked about sparse parameters, and in this case, we're we would update all of the parameters in the bias, but just those parameters. So we are no longer looking at just a sparse update here. Here they also found that particularly the kind of most important biases to update in your model are actually the bias parameters associated with the query matrix in the multi-layer attention layer in the transformer, as well as the second multi-layer perceptron in the transformer layer. Now, kind of the structure or using structure in your model is actually quite general and can be combined also with these sparse methods that I mentioned before. So for instance, in computer vision, people have pruned entire groups, such as certain filters in CNN models. And there have also been quite a few recent studies that looked at pruning certain parts of your model. For instance, by pruning in BERT, it's been quite popular to prune certain attention heads, where people have observed that if you look at actually the distribution of attention heads in your BERT model, and here basically you look at the performance on multi-NLI, if you just prune each of the attention heads in your model, and you can actually see that from the performance where you have like all of the attention heads, in a lot of cases the performance like drops, but only slightly when removing an attention head. But in some cases it can actually be lead to a positive improvement by removing an attention head. So in practice you can remove quite a substantial fraction of these attention heads of your BERT model in practice. So basically the main point of this section is actually that the information of the structure of the model is quite widely applicable. For instance, another method, diff pruning, that I just mentioned before in this past section, also proposed a structured variation, which basically can share the mask between different groups in the model, so different kind of weight matrices in the model as well, because arguably having similar masks between different kind of similar representations can also be useful or can be informative when learning those masks. And in the next sections, I'm also going to talk more about other methods that use the structured information in different ways. So finally, coming kind of towards the final part of this parameter composition section, there are also low rank methods. So low rank methods basically you can view as having your modular parameters kind of lie in a low dimensional kind of subspace, a low dimensional space, which can kind of be another useful bias because it allows you to kind of constrain your optimization problem and make that kind of simpler or simpler to optimize and simpler to find kind of a local optimum in practice. One kind of very influential or very kind of insightful study in this area has been a study by Lee et al. At ICLR, which essentially showed that kind of for any model, you can optimize this model in a low dimensional randomly oriented subspace and for many models kind of achieve reasonable performance if the subspace is kind of sufficiently large. So what this means in practice, so we can see this kind of in the relation to standard fine-tuning, where in standard fine-tuning you basically have your existing pre-trained initialization, and you basically learn how you want to update it. So you learn basically this task-specific update vector that you can add, or how you modify your existing pre-trained parameters, theta 0 here. And in practice, how this looks like, kind of just schematically shown here in a three-dimensional optimization space, is that you have your pre-trained initialization, and using your kind of update vector, you move then towards your kind of target final fine-tuned set of parameters. Now, in this kind of low-rank optimization, instead, we essentially have a similar formulation, but instead of having basically this update vector being the same dimensionality as our original parameters, so having the same dimensionality d here, we have a kind of a low rank update, or kind of a smaller dimensional update that we learn, kind of where the small d is a lot smaller than the large d. And we have an additional projection matrix that projects from kind of this full parameter space into our low dimensional space, which is kind of random because we're using kind of a randomly oriented subspace that we're learning. So in practice, this can basically be shown as simply having a hyperplane here that projects into our small dimensional space, in this case, just from 3 dimensions in 2 dimensions, where now our optimization problem is just now, instead of having all of these 3 dimensions of freedom, we now only have two-dimensional freedom here. Yeah. So with this kind of same image in mind, we can basically apply the same thing now to very high-dimensional models, where instead of having 3 in 2 dimensions, we now have kind of millions of parameters of our original model, and now kind of a small number of parameters, say maybe only 1,000 parameters for actually performing our modular update. And again, here, kind of the main thing to note is that the only thing that we're learning is this now very low dimensional update. So in this case, we're only basically updating 2 parameters, and all the other, everything else is fixed. So both of these, the original pre-trained initialization is fixed, as well as this random matrix is also fixed. So this is something that is kind of randomly generated. So in our notation, basically, this kind of just looks like this here, where we have our original parameters theta, and then we add another, our modular parameters phi here, where our parameters phi are now just projected using this random projection matrix P here. The kind of main downside of this, or one kind of practical challenge of this general method, is that if you try to apply this to very large pre-trained models, which have in the hundreds of millions or even billions parameters, it's very, very expensive to actually have to compute or keep in memory this huge projection matrix that is, yeah, kind of O of D. So that needs to project from all of the huge parameters still into a smaller subset. So for large models, we really need some kind of way in order to really scale this method. We need something that is more efficient in practice. And kind of one way, so one way we can do this is by basically using matrix factorization, and in particular, kind of very specific form of matrix factorization. So instead of having to store this huge matrix P explicitly, we can simply decompose that into a set of smaller matrices. And kind of in practice, there's for these, like for having these properties of the random matrix, there is kind of there are some methods that have been proposed in the past in order to compute this efficiently. And one method that has also been used in this work by Lee et al. Is known as the fast food transform. And yeah, don't ask me why that is named that way. So in their paper, they basically showed that by using this very efficient matrix decomposition, we can essentially kind of remove or very much reduce the size of the parameters for O D times D to O of D, and also reduce the time it takes to compute it quite significantly. And here, just for completeness, basically the way this matrix is factorized is essentially as a sequence of a number of different random matrices with different properties, which are all kind of multiplied together. So yeah, if you want to have more information why this works, you can kind of check out the paper of Lee et al. or this paper for the mathematical details. So kind of having said that, now I've kind of talked about like the mathematical intuition, but the actual more interesting thing is what this can actually tell us about our models and the parameter space that, or the kind of low dimensional parameter space that these models actually live in. So in Lee et al, they basically defined kind of as the intrinsic dimensionality of a model for a given task as kind of the number of dimensions that we need to optimize in this randomly oriented low dimensional subspace. That will allow us to get within 90%, so within kind of a reasonable margin of performance to the performance of fine-tuning the full model. And for our purposes, they basically looked at a couple of different tasks in computer vision. But for our purposes, it's more interesting to look at a recent paper that kind of used the same formulation, but looked at pre-trained models across a variety of different NLP tasks. And the main kind of high-level observations that they made here is that kind of overall, if you look at the progress or the intrinsic dimensionality of these models over the course of pre-training, models actually kind of implicitly minimize this intrinsic dimensionality over the course of pre-training. So the original kind of close to random model would need kind of a lot of parameters in this low dimensional subspace in order to actually optimize this for the task. But for the model that has already learned very general purpose representations, you can actually only need a small set of parameters and actually to get very good performance on a given task. And larger models, because they're much more over parameterized, parameterized, allow you to use even a smaller set of parameters. So here we can basically just look at a general plot where we can basically see different models plotted based on the number of parameters, where you can see basically smaller models like Albert on the left and larger models like T5 3 billion on the right, with regards to how they perform on just one task, MRPC, and with regard to their intrinsic dimensionality on the task. And we can see basically here that this intrinsic dimensionality is very much correlated with the size of these models. So as we scale up these models like overall in the size of these models, we only kind of need a very small number, so close to like between 100 and 1,000 dimensions that we actually need to update of these models in practice. I've already mentioned that structure is something that can be that is quite applicable to many different settings. So they also proposed a structured variant, which is basically quite simple. So in addition to having this projection matrix, they basically just define another scalar parameter per layer that is just learned in addition. So for each layer now, we have here, so for each layer index I here, we basically have kind of learned a separate scalar here that we just multiply with our parameters, just so the model at least has a very simple means of deciding which layers are more important and which layers it should kind of give more attention to. And this also, just including this very simple structure information, also kind of improves performance in practice, or improves kind of the intrinsic dimension in practice as they've observed. However, kind of the main downside, and why I think most of these types of methods have mostly been reduced kind of to the analysis part, is that actually storing these random matrices is still, even though we use these fast food transform, which is more efficient already, storing these random matrices is still quite expensive. So it still requires a lot of space and still is quite slow to train, because we still need to kind of use this huge projection in practice to project our parameters into this low dimensional subspace. So kind of as a kind of alternative, we can try to apply this low rank constraint also not just to all of the parameters of the model, but again to just a subset of the model parameters. And here, one method that basically proposed that is LoRa, which is low rank adaptation, which kind of in addition also learns the projection matrix directly. So instead of using a random matrix here, they actually kind of treat the projection matrix as trainable parameters as well, if they are small enough. So the low rank update here basically, so instead of before having this like small set of parameters and your huge random matrix, we instead basically just define like two low rank matrices that we can then multiply together to kind of get a low rank update. And in their case, in their formulation, because they really apply this only on the level of individual weight matrices, so basically for kind of an update, just looking at a particular weight matrix in a feed-forward layer, you have here again the original initialization and your kind of the update that you've learned. And in the LoRa setting here, you basically just decompose this update that you've learned into these two separate low rank weight matrices now. So here basically, yeah, this is just kind of the matrix rank, the hidden dimension, and then the input dimension of the model. And just schematically, just to make that a bit clearer, you can basically see this as having your pre-trained or your original pre-trained weight matrix here, and then your kind of low rank update. So the kind of two smaller weight matrices that you can then just update or add to the original weight matrix to get then the final either the final hidden state here or like a final weight matrix in practice. So in our case, just because we looked at, instead of looking at weight matrix, we looked at just the general like parameter vector. So in order to kind of express that again in our notation, we basically just need to like vectorize that. So instead of treating this as like a weight matrix update, we just treat this as a single vector that we can also again just add to our original parameters here. Cool. So now, just as a just brief summary of the methods in this section, this is again just all of the notation that we mentioned. And as we can see here, the sparse networks, subnetworks are kind of the most diverse in terms of the way that they've been implemented, where we both have kind of the way of just adding the sparse vector to our parameters, where we can additionally zero our parameters to zero, the pruned ones, or where we can just only apply the mask directly. And kind of secondly, we have our structural representations, which are only applied to certain subsets, certain groups of the model. And finally, kind of our low rank composition, where we either have a random matrix or kind of our low rank representation in the end. Cool. So with that, I think here it's just kind of a rough comparison, and just this should mainly serve as a general guideline and rule of thumb in terms of the different properties of these methods. So looking at different dimensions here, and in particular, so one advantage of these methods is that they are very parameter efficient, so they only add a very small number of parameters. However, in practice, as I already mentioned, pruning typically requires multiple iterations of retraining. So during training, at least, this is more expensive at an inference, because we can simply add these additional parameters to our model. They do not actually increase the model size. And recent methods like LoRa have actually demonstrated quite strong performance on different tasks. And finally, some other work has also shown that these subnetworks can be composed. So in general, we can kind of have generally kind of positive performance, and only in the level of training efficiency here we have some deficiencies. But again, here this is something that is kind of mainly meant as like a high-level view of these this kind of family of methods, and may differ for individual methods, or some methods may kind of seek to improve on particular aspects here. Cool. Now coming to the second part, and the two next parts here are a bit shorter in general. So for input composition here, these type of methods, as I already mentioned, basically instead of modifying and adding parameters, we simply augment the input of our model with a learnable parameter vector via concatenation. Standard prompting, as we've already spoken about before, because we basically define kind of this human-defined prompt that is then fed into our model. So the prompt is effectively embedded using our embedding layer. So you can even view this standard prompting as kind of a way of this input concatenation, because as a prompt, as a result of getting this prompt, by embedding it with our model's embedding layer, we again kind of produce or obtain some parameter vectors phi here that are concatenated with the input. However, as we've already talked about, defining this prompt with text directly is subject to a number of different limitations. So in practice, kind of the more robust way is actually, instead of using like text to define a prompt, to try to learn the prompt directly in a continuous manner, and then prepend this continuous prompt to the input. So you can view that basically here in kind of compared to standard fine-tuning, where again in standard fine-tuning you fine-tune all of the parameters of the model based on your input kind of specification here, and continuous prompting or prompt tuning here, in contrast, basically uses the same input again, which is kind of embedded in our model, and in addition kind of concatenates or prepends to the front of it a small number of additional embeddings that make up our continuous prompt here. And as you can see here, now the prompt is not just a parameter vector, but basically can consist of multiple embeddings. So it's effectively kind of a matrix as a sequence of these prompt embeddings. However, one downside that people have found with this prompt tuning is that in general, because the only way you interact with your model is at the input layer, so the amount of capacity that is available to your model to actually adapt to the task is quite limited in practice. So because of this, prompt tuning has mostly been effective. So just as prompt tuning, where we add a continuous prompt in the input, has mostly been effective at the larger scale of models. So here you can basically see kind of different models as we scale up the number of parameters in terms of their superglue performance, compared to just prompt design, where we define the task-specific prompt. compared to standard fine-tuning, and looking at the performance of prompt tuning here. And as we can see, all the way until like only at the very largest parameter size here, are we able to match the performance of full fine-tuning using prompt tuning. And at all the other parameter sizes, prompt tuning actually underperforms fine-tuning the full model. However, there's kind of one simple way, or one way that you can use, still do prompt tuning and induce, give more capacity to the model, which is by including the prompt not just at the input, but at every layer of the model. So here you can basically see this kind of represented. Again, we have the standard prompt tuning where we only add this predefined prompt that we have here. And we only get representation for that are considered in the first layer of the model. And then all the subsequent representations of the model are basically kind of conditioned and computed based on this initial representation that we can learn. And now, in contrast, in multi-layer prompting, we are essentially providing additional kind of tunable prompts at every layer of the model. So now we're not computing all of the prompt parameters based on just the initial parameters here, but learning all of these kind of multi-layer prompts as well. And kind of studies that use these kind of multi-layer prompts have basically shown that including the prompts, particularly at the later layers, is more important because, as we know, in the later layers, these models are kind of more important to adapt. In practice, kind of one implementation detail here, the way these prompts have been kind of implemented in a transformer layer, kind of in practice, is by simply kind of prepending them just to the keys and value matrix in your attention, which is kind of more efficient or kind of more amenable to like the implementation frameworks. So here, just as a comparison with regard to the parameter composition from before, prompts or continuous prompts as well have the advantage of only adding a small number of additional parameters. In practice, however, because we add these parameters by extending the context window, so by extending the input of a model, this kind of leads to more like inefficiency, both during training as well as doing inference, because now our model needs to respect kind of a comparatively larger input. So the same downside as with the additional kind of discrete prompting as well. We have here for performance, again, as I mentioned, the standard prompt tuning requires comparatively large models to perform well. And at least so far, and I think this is something that has actually changed recently, there's not been very much work on actually composing these different prompts in practice. So here, basically, in terms of parameter efficiency, I think they're one of the most efficient methods actually, but are kind of more inefficient both during training and inference, and also kind of slightly worse performing at smaller model sizes. Cool. So with that, we're now coming kind of to the large family of models here, which is function composition. And function composition basically can be seen kind of as the most general framework where we essentially define, or we can define kind of an arbitrary new function that we use our new parameters phi to parameterize. In practice, kind of if you talk about adding kind of arbitrary functions into a model, that is something that has been kind of very well studied in multitask learning, where kind of people have combined different modules and with different sharing patterns across a diversity of different tasks. But in this case, so if you're interested in that, I would mainly kind of direct you to these two surveys, because in this case, because we're studying or mainly focusing on pre-trained models, which is not typically the setting most multitask learning work takes place in. And kind of the most prominent work in this setting of adding kind of additional parameters to the model, because the main purpose of these additional functions is essentially to adapt the model to downstream task. These functions are also typically kind of referred to as adapters. And the design of these adapters is typically kind of based or dependent on the architecture of the underlying model. So kind of the earliest adapters, or kind of one early set of adapters has been proposed for computer vision, for kind of standard ResNets. And in this case, basically the adapters consisted of a batch normalization and a one-by-one convolutional operation, because this is kind of the most, or one of the most effective ways to kind of deal with the input modality of images in computer vision. In NLP, adapters have been mostly applied within and added to kind of pre-trained transformer models like BERT. And in this case, the most common formulation of an adapter layer that you can see here is basically consisting of a down projection, so simple linear feed-forward layer, a up projection coupled with a non-linearity that is connected with the rest of the model via a residual connection. And for this non-linearity, different variants have been explored, but the most common one that is used in practice in many approaches is simply a ReLU unit. The adapter, kind of different approaches have placed this in different parts of the model. And it's typically either placed after the multi-head attention layer here, or after the feed-forward layer, or after both. And most approaches in NLP that use this adapter formulation have basically kind of made little modifications to this underlying bottleneck architecture. There's kind of one recent modification that can be that we can mention here, which essentially combines kind of this low rank assumption or kind of this low rank intuition that I mentioned before with the formulation of adapters by essentially reparameterizing our linear matrices in the adapter layer with low rank approximations. And in this case, they kind of use a particular formulation that uses that similar to LoRa from before, uses kind of low rank matrices here, but that are now combined via kind of an outer product or Kronecker product here to basically kind of extend their size to the full parameters that we would actually like to have in our adapter layer. And with the additional kind of, with additionally having some structure information in there that part of the adapter layer, so part of these, so one matrix here, the A matrix, is shared between all layers of the model. So this is something where the model can learn some commonality across different layers, whereas the other matrix is kind of a low rank matrix. So it represents basically the assumption that we've seen before about kind of optimizing our models in a comparatively low rank subspace. And the hyperparameter basically is just with regard to this formulation of which has been used in hypercomplex multiplication, which basically allows you to get a the higher your n is, the higher this is kind of an the approximation. And this is kind of a hyperparameter that you can use to modulate the capacity or expressivity of this method, and is typically between 4 and 12 in kind of the proposed methods here. And in practice, by using kind of this like formulation or this decomposition, they've basically shown that they could reduce the number of adapter parameters by a factor of 10, but still keeping either the same or even slightly improved performance through these additional inductive biases. Now adapters can also, in addition to their position, you can also decide how you want to include them into the rest of the model. So they can be either routed sequentially or in parallel. Before I've just shown the sequential adapter here, which essentially inserts the model, inserts in adapter parameter kind of on top of the existing stack of the functions in the model. But you can also have it in parallel, where the model can basically decide and where the output of the adapter parameter is just added to the output of the existing model directly. And in practice, typically most approaches have used these sequential formulation, but some recent work has actually shown that parallel formulation might actually work better in some settings. There are also kind of some other benefits of adapters in general, and some of these also translate to like other modular methods, but just adapters have kind of been most studied in practice, which is why yeah, most of these benefits have been shown for adapters so far. And in particular, because for many of these modular models, you optimize parameters, the parameters of the model not in the full space, but only a small subset of parameters. So because that constrains the optimization problem, this can actually lead to more robustness in different settings. So for instance, in one study, they looked at, I think, one kind of well-known failure mode of BERT, which was its kind of very sensitivity to certain learning rates in different tasks, particularly in light of small amounts of data, particularly for COLA and MLI here, where you can see here for full fine-tuning in some settings with certain learning rates, you get a very high variance in terms of performance. And in comparison, if we look at just adapters, you can see that even across a wide range of different learning rates, the performance stays more or less kind of in the same ballpark. In addition, methods have also shown that these kind of modular methods like adapters really excel in very small, low resource settings. So applying kind of here, just one example method in a low resource setting compared to full fine-tuning actually allows you to be much more efficient, again, because you only need to update a small set of parameters here. Now, you do not actually need to add or learn a whole new function to be kind of effective in this kind of function composition or in this adaptation regime. So you can also get away with simply just learning some scalars or simply parameter vector to multiply with your existing parameters of the model via element-wise multiplication. And this is something that has been kind of most commonly applied in to certain normalization layers, where people have simply kind of modified them using multiplication either for batch normalization or layer normalization in NLP. And by basically doing this sort of rescaling, this essentially allows the model to select which of these parameters, which of the existing parameters are most important and should kind of be upweighted versus downweighted, which can already be quite powerful with these like very large models in practice. And this is also something that is quite compatible with these other methods. So even LoRa, for instance, in kind of an updated formulation, includes a rescaling component as kind of a scalar that is simply multiplied with the output of the weight matrix here. One recent method that kind of takes this rescaling idea and applies it to certain parts of the transformer is IA cubed, which basically simply learns vectors here. So it just learns separate vectors for the feed-forward layer in the model and the keys and the value matrices in the multi-head attention layer that are simply multiplied with the output, so with the hidden representations of the model here. And doing this simple rescaling in very specific parts of the model, again, kind of with information of the structure of the model in mind, also allowed them to achieve very strong performance in practice. So here, again, on a high level, we can see kind of function composition kind of compared roughly towards these other methods on different properties. And one downside of adapters is that because they use this bottleneck layer, which depends on the hidden dimension, so with very large models, they will have to allocate kind of a larger number of parameters compared to some of these other methods. In practice, however, they can be more efficient to update because you only need to update, you only need to consider the gradients of these adapter layers. So these are only very concentrated in certain parts of the model. In practice, like at inference, because you add these additional functions in the model, they slightly increase the number of operations that you need to perform. But they typically match or outperform standard fine-tuning, and they've also been composed in practice. So we can see here, again, kind of a slightly different performance profile or slightly different strengths and weaknesses here. Before I'm getting to the end of my section, I just want to give kind of a couple of other high-level ideas that are connected to all the different sections so far. And one general idea is parameter generation for these modules. So so far, we've basically directly optimized these particular parameters phi for every individual task, kind of separately. So if we update our pre-trained model for one task, we learn these parameters for that one task. And if we now have a new task, we learn again new phi parameters for that new task, but all of that in isolation. However, as we will know from multitask learning, many different tasks share kind of some underlying structure. So it would also be helpful to have some means of enabling some positive transfer between these modular parameters. And in practice, kind of one way that has been achieved so far is using kind of a hypernetwork. So using kind of a small neural network that can be used, that can be now optimized separately, and that is used to then generate these parameters, for instance, the adapter parameters here. So we can use a hypernetwork to generate basically parameter vector that we can then reshape into our feed-forward up and down projection that we can then insert as an adapter layer into our final model. And these adapter networks, as you can imagine, are most effective when you can generate them on data that is actually relevant for the target task. So in general, so far, these hypernetworks have been applied to basically all of these previous methods. So they've been applied to generate both just maybe the final classify heads in the model. They've been applied to generate continuous prompts as well as adapter layers in different settings. And they've also been conditioned on kind of many different forms of metadata. Typically, the kind of most standard setting is learning a task embedding. So kind of now as trainable parameters, you have a representation for each task that you learn. In the multilingual setting, people have learned language embeddings. And in order to make this hypernetwork more efficient, because now again, you have these kind of additional parameters that you need to learn every time you want to generate, say, these adapter parameters, you can additionally condition them on the layer ID in order to share and use the same hypernetwork for your entire model now, which can be very parameter efficient in practice. Finally, all of these methods, as I mentioned already, they share and they are kind of many different ideas or kind of built on similar like high-level themes. And of course, they're not, many of them are orthogonal, so they can be kind of combined effectively in practice as well. So one recent kind of framework, for instance, here showed basically the similarity between different methods. And in particular here, they showed that kind of representative methods of these different sections, so LoRa, multi-layer prompt tuning, as well as adapters, can actually be expressed in a very similar functional form. And specifically kind of as similar to function compositions as modifying the hidden representation of a model. And I'm not going to go like too much into depth here because particularly for prefix tuning, that just requires kind of deriving the particular form here based on kind of modifying a bit the how this prefix tuning is added and is applied in the multi-head attention layer in the model, which can get a bit involved. But in general, you can see these basically all as adding a parameter vector here, in the LoRa case with a scaling function here, and in the prefix tuning case by some sort of weighted combination based on the normalization parameters of the softmax, and all of them basically taking kind of a form ultimately that can be expressed, at least in this in the confines of a transformer layer, through some combination of a different weight matrices in the adapter with the formulation that I mentioned, with LoRa with these two weight matrices applied to the input, and for prefix tuning actually kind of incorporated into the softmax formulation in the attention layer. Now, because all of these methods are like orthogonal to the with each other, we can also combine them in the same framework, and they're actually kind of complementary, and as I mentioned, have different strengths and weaknesses. So we can combine, so a recent approach, for instance, combines all of them in the same model by essentially using kind of LoRa, prefix tuning, and adapters here in the same, the adapter should be on top here, in the same model, and simply both learning these separate modular parameters for each instance, as well as learning separate gating parameters, which are essentially just scalars that allow the model to weight the contribution of each of these different parameter efficient methods. And they show that, again, kind of the combination of these different methods actually performs better than any individual one. Again, here, all of these kind of concepts can be kind of combined. In particular, some of these high-level ideas like sparsity, structure, rescaling, or low-rank approximation are quite kind of generally useful and kind of composable and combinable in practice. So here et al., for instance, also highlighted kind of different variants of adapters that so far have been kind of not really very well explored, such as the adapter on E here. So here is basically just kind of adapter. Prefix tuning is expressed as in an adapter formulation LoRa, the parallel adapter variant that I mentioned, and basically just an adapter with an additional kind of scaling parameter here, which can be kind of seen as a combination of an adapter and kind of the LoRa embedding layer here, where the main difference is now that we don't have a nonlinearity in LoRa, whereas we have the relu nonlinearity in our adapter layer. So many of these methods are actually kind of, if you look under the hood, kind of very similar or share a lot of like the high level ideas. Cool. So now just for the final words in this section, I'm just going to end with basically, I already mentioned like the high level comparison, but I just want to give you briefly kind of a high level overview of how these different methods compare to each other in terms of their performance. And here, this is basically based on two different studies, one from Mahabadi et al. And one from Liu et al. Here. And the nice thing is both of them basically use kind of the same different tasks, but kind of the same axis. So they're quite kind of comparable side by side. And indeed, kind of both have different methods here represented in terms of the number of parameters that they kind of add or learn for each new task, where in both cases, we basically have here the like full fine-tuned model, which adds like 100% of parameters. And in this case, we have like the performance of the full fine-tuned model here. And in this case, we also see kind of the memory consumption of each model indicated by the size of the circle. And so for each method, some of the main kind of methods are represented in these comparisons. And we can first see that for prompting, prompt tuning, as we already mentioned before, applying this to kind of a standard, so this is like a 200 million parameter model and a 3 billion parameter model, but even in for the 3 billion parameter setting, it actually leads to quite reduced performance, even though it has adds a very small number of parameters. Secondly, we can see here that for the intrinsic dimensionality method, this adds like the lowest number of parameters because we have this kind of very efficient way in which we can define this random matrix, but achieves lower performance compared to these competing methods. And if we look at memory consumption, is quite expensive in practice. If we look at fine-tuning biases in terms of bit fit, this adds kind of a smaller number of parameters, but still kind of achieves lower performance compared to the other methods. And finally, kind of the set of methods that performs best in practice are kind of these most general like function composition methods, where we can see basically here different adapter variants and compactor, and we can see here compactor and IA cubed, which kind of so far at least have the best trade-off in terms of performance and additional parameters added to the model. Cool. All right. So with that, this kind of concludes the first part of the section here, focusing mainly on kind of the computation functions. And I can hand over now to Jonas, who is going to cover the second part of the talk.
Thank you very much, Sebastian. Just a quick question. Is there going to be a coffee break or should we?
Yeah. Okay. Should we break now or? Yeah. Okay. Yeah. Cool. So let's have maybe a 15-minute coffee break. Hey Jonas, are you there? Are you?
Yep, I'm there.
Awesome. Do you want to share your slides?
Cool.
Cool. Awesome. So yeah, I think the room here, I don't think you can see the room here.
No.
But yeah, it's filling. People are almost back. And yeah, so I didn't mention before in terms of questions, again, just to recap, I think you can stick around later and ask questions, or if you have questions for the other presenters who cannot be here in person, you can ask them on yeah, ideally probably in Rocket Chat, because I guess the questions in Zoom will maybe disappear in the end. Yeah. So yeah, just use that, and or talk to me or some of them throughout the conference. Cool. All right. So Jonas, the floor is yours.
Yeah, thank you so much, Sebastian, for the amazing introduction to the computation function. I will be talking about the routing and aggregation concepts, and then and this is kind of where we'll draw the connection more to this modular aspect of these parameter efficient models methods that Sebastian has talked about. So just a quick recap of the concepts of what Sebastian has been talking about on the parameter level, on the input level, and on the function level. We've kind of talked about how we can learn the information or the specific task that we're interested in subparts of the model, in the sense that a lot of these parameters that of the pre-trained model, for example, are frozen, and we have a set of specific task-specific weights that are associated with the objective that we're training on, and in that essence, for the subnetworks, we have this masking operation that is associated with that specific task. So only this specific mask is necessary for us to know for a specific task. Whereas on the prefix tuning level, we have these input vectors that are associated with a specific task. And finally, on the function level, we have these layers that we've added to the model. So each kind of concept has a set of defined functions that are associated with this task, whereas the majority of parameters and the majority of logic is actually shared across tasks if we're interested in multiple different tasks. And so in order for us to understand which parts of these concepts are task specific, we can actually try to make this as a more general kind of illustration, because in its essence, all of these methods actually are somewhat modular components, even though that the underlying logic is somewhat different. So in order for us to talk about routing in a more general way, we're gonna just have a broader overview of this and illustrate them as a very similar concept. And so we have these gray boxes indicating these modules, and they will be able to be used for any of the modular components that Sebastian has talked about in the first part of this tutorial. So the question now is, if we have a set of different modules that we have available, how do we, if we have this set of modules, how do we make the decision at the input which of these modules we have to select? So for a given task, for example, which module should we select and which module should we pass through the representations next? And if we provide this with a notation, then we can define F as the set of modules that we have available, again, associated with these gray boxes. And these are the modules that we have to make a selection over and make the decision which modules to select. Okay, so from a very high level perspective, we can say that we define a routing function which outputs a weight, a scalar selection of the respective modules. So basically the edge between the router and the respective modules that it can decide over is associated with this weight alpha. And there are many different concepts and many research directions that we can follow here in order to make these decisions. First of all, there's fixed routing, and this is basically a scenario where we make the decision before training, so a priori. And on the other hand, we have learned routing, where we give the router actually the capacity to learn something from the data, so basically to learn to route. First, we'll look at this fixed routing scenario. So as I just mentioned, the routing decision is actually made a priori. So that means before we even start training, we actually make the decision which module should be selected at the respective point of time. So we have a one hot or k hot selection, where k is the set of modules that we want to use for an input, and 0 otherwise. So basically, if we have a one hot selection for each individual input, then we have made the decision that alpha 3 in this specific scenario, module 3 should be selected for that specific input. And the router does not actually have any capacity to learn anything, because we already have made this decision before. So a bit of an illustrative example, just let's imagine that we perform multitask learning, for example, using BERT, and we have 3 different tasks that we're interested in: NLI, named entity recognition, and question answering. And we have the corresponding prediction heads that are associated with each of these individual tasks. Now, if we pass an example of NLI through the model, then the representations are passed through the entire BERT model. And at the final layer, we have to make a decision which prediction head we will actually use. And this decision can be made based on the metadata that we have available. We know that we're passing an example of NLI through the model. So the router, in that sense, selects the NLI prediction head to pass the final representation of BERT into that prediction head. And the same routing decision is made for named entity recognition and question answering. So in that sense, the router is not an explicit kind of function, but actually, we correspondingly route the examples to the model, to the prediction head, depending on the task information that we have available. Another scenario where we perform fixed routing that might not actually be immediately apparent is all these parameter efficient fine-tuning strategies, where we freeze the majority of parameters and only fine-tune a small subset of weights. And that is because we are freezing the parameters of the shared parts of the model. We actually make this selection that we fine-tune a subset of parameters on that specific task. So from that perspective, this results in these parameter efficient strategies, because we can pull out and disentangle these, for example, adapter layers from the pre-trained model, and only store them separately. So even though we're training different modular components, different adapters on different tasks, the surrounding parameters remain the same, and so we don't need to store them. So yeah, for example, these adapter layers only correspond to 3 megabytes of data, and even less depending on the method that you're using and what Sebastian has talked about earlier, whereas these shared parameters require much more storage space and are kind of any type of architecture can be used here. So from that perspective, frameworks like the Adapter Hub are an ever-evolving multitask model. So the Adapter Hub is a framework that builds on Hugging Face transformers. And the concept here is that a user can download the pre-trained weights of, for example, BERT or Roberta or T5 or any type of pre-trained model that we're interested in, and we stitch in these adapter weights or any type of parameter efficient fine-tuning scenarios. And then the user actually starts to train these adapters, again, freezing the pre-trained weights. And because the pre-trained weights are actually frozen, we can extract these adapter weights from the architecture itself, and for example, upload them to the Adapter Hub, where a new user can find this adapter that they're currently interested in because they have a similar task, and then download the pre-trained weights from Hugging Face because they have not actually been updated, and stitch in these fine-tuned adapter weights that the first user has fine-tuned and perform inference. And this cycle of loading the same adapter, same transformer, same pre-trained weights from the transformer, adding these adapter weights to the model, and continuously increasing the number of adapters that we have available on this shared framework actually distributes the training of this multitasking model across the community. And even though that these modules are trained by many different users, the freezing of the pre-trained weights essentially is resulting in us performing multitask learning. And because of the freezing, the routing decision is made basically in a fixed manner, what I've discussed right now, because only those newly introduced weights are updated and when we basically look at the framework on the Adapter Hub, which includes hundreds of adapters, then we know which type of adapter should be selected for the respective task, because the metadata that we have available for a specific adapter basically lets us select an adapter for that specific task in a fixed manner. Okay, so that is one way of routing, in the sense that if we want to utilize metadata that we have available and make this decision a priori because we have the metadata available, then this is one way to go forward. Alternatively, if we do not have metadata available or want to provide the model with more capacity to actually disentangle, for example, knowledge of heterogeneous data, then we will have to look at learned routing. And here, again, we have two different directions that we can look into. First of all, there's hard learned routing and soft learned routing, where hard learned routing somewhat simulates the fixed routing decision, so a hard selection of modules, and the soft learned routing relaxes that slightly. So the learned routing in general parameterizes the routing function, which is again like very interesting if we do not want to make this routing decision a priori. So the parameterized router actually has the capacity to learn from the data, And the input to this router can, again, be something like the task information, but we can also pass in the features of the input example. So based on that, the router can learn to make these alpha decisions during training. Now, learning to route comes with some challenges, and Rosenbaum et al. Provide a great overview of that. In specifically, one challenge that we often see during learning to route is training instability. So imagine that we are actually training this routing network together with the modules from a random initialization. Then the router, which is randomly initialized, has to make a decision which module, which is also randomly initialized, is most useful for the input example. So there is no kind of information that the module actually incorporates. And so what often happens is that these routing dynamics never stabilize, meaning that the router has no reason to select one module over the other. And there are some methods like freezing parts of the model during training and so on that aim at mitigating this. But in general, yeah, these routing dynamics are often kind of difficult to train, especially if we're starting with a completely untrained model. Second of all, module collapse happens. So that is that the router falls into a local optimum and only selects a small subset of the modules that it has available. So in the plot that we see on the right, the top plot is the ideal scenario. So we have a linear function that the red module learns, and respectively a green module. And this is kind of the ideal scenario. Two modules are learned to approximate these two functions. The problem is that in the second example, what we have here, that potentially the module, the router only selects a single module because it has collapsed in that sense, and only selects a single module that tries to approximate this specific function, and that is with a linear function just not possible. So the function that approximates this is just not optimal, even though that the entire capacity of the model would have had the potential to learn the separate modules for that. The router has fallen into this local optimum and only selected a single module for all examples. Thirdly, because and this is kind of the directly opposite problem that can occur is overfitting, because we provide the model with maybe a large number of modules and it can route the examples respectively. We have the risk that through these dynamics of routing and many module functions, that the model overfits to noise and learns a large number of modules for every single small example. And this might also have detrimental effects on the generalization capabilities of the model. Okay, so these are problems that can occur during learning to route. And in order for us to actually try to perform this routing, we can first of all look at hard-learned routing. And here, as many of you know, making these discrete decisions is not directly trainable with vanilla gradient descent, because we cannot backprop through this discrete selection of a categorical distribution. And so there are some methods such as policy gradients in reinforcement learning that we can use in order to make these discrete decisions. This has been done, for example, in routing networks, modular networks, and compositional recursive learners. There are also evolutionary algorithms such as PathNet and MuNet, and stochastic reparameterization approaches such as AdaShare and Polytropon, which all try to learn these discrete decisions. For example, the Polytropon uses the Gumbel softmax, which uses the reparameterization trick in order to learn this to learn a categorical distribution over the selection, and they specifically learn a set of modules, in their specific case LoRa modules, that they make this hard decision over, and the model has the capacity to combine multiple LoRa adapters to solve a multitask learning scenario. Second of all, there is soft-learned routing. And in soft-learned routing, we try to sidestep this discrete selection of modules, and instead the router learns actually a probability distribution over the available modules. So the available modules is the set of F. And basically, instead of making this hard decision of somewhat of a k-hot encoding, we learn a distribution over the modules. So in this illustration here, we have each edge associated, with a scalar weight that identifies how high each of these modules should be weighted. And many of you probably know the mixture of experts type of learned routing, where the output of each of the modules is weighted with the activation of the router and summed over. So we basically have a weighted average over all the modules, where the weighting is decided by the router specifically. The problem with this type of scenario is that we are actually activating all the modules at all times. So we have to pass through every single module, and the only decision that the router makes is how highly this specific representation, the output representation of each of these modules, should be weighted. And this significantly increases the computational cost for this type of operation, because we're actually, as we in the hard-learned routing or fixed routing scenario, we have made the decision for only a subset of modules. Now we actually have to pass through all modules and weight the representations accordingly, and that's very computationally expensive. Mitigate that, some approaches propose top K routing, and as the name says, we only select the top number of modules, and this forces us to renormalize the weighting, because now we do not select all of the modules anymore. We only select a smaller subset of those. Basically, if we look at the illustration from earlier, we would then cancel out the selection of the first module and only average over the second and third module. So this again decreases the computational overhead, because even though we have this distribution over all modules, we will just only select a small subset of those. This can be driven to the extreme, for example, in switch transformer by Fedos et al., where they only select a single module, and so only the top module is selected, And yeah, this simplifies this scenario even more. Basically, only a single module is selected, and this is an approximation of the categorical selection or hard selection of the modules. The problem with this specific scenario is that we will talk about the specific use case of Fedos et al. And switch transformer. But in general, if you do not have a lot of training data available and just perform this top one routing, then most likely you will have module collapse or other problems during training, because again, like, you don't have this stochasticity during training that different modules might be selected, because you're always only selecting a single argmax module, and no randomness is included in training here. So most likely, in a naive implementation of top one routing in this scenario, you will face some of the challenges that I talked about earlier. Now, let's look at this specific example of top one routing more specifically. This has been proposed especially for the switch transformer, where actually from the module perspective, the feed-forward layer is of a vanilla transformer is considered as the module, also known as the expert. And so the only parameters that are shared across all kind of all examples are consists of the multi-head attention layer, and every single token is routed to a different module. So let's, for example, take as an example the sentence routing on the token level. Then every single token of that sentence is routed to the multi-head attention layer, then to the router, and this router selects a single expert or module for that specific token. Not more than one, exactly one module is selected for each token, and that is done for every single token in the example. Now, because the objective of these approaches is not modularity, but actually an efficient training of these very deep models. So the idea is to sparsely activate a large set of experts, and in order for this to work, the load balancing has to be implemented, meaning that ideally, we want to uniformly distribute these tokens across hardware accelerators, meaning that every single token, if we place these different modules on different hardware accelerators, then ideally every single hardware accelerator should receive the same number of tokens at every single layer in order for this to be efficiently implemented from a hardware perspective. So this load balancing has also been the focus of some research recently, where the first way of implementing it was that each token selects the top K experts that it wants to be routed to. So each token selects the expert. Alternatively, the experts can select the top K tokens that they want to be routed to them. And in the base layers, a global decision is made across all tokens and across all experts. The problem is that because of this load balancing, we restrict the model from actually routing all the examples of one sentence to the same expert. So because of this load balancing constraint, we can never route one specific token, all the tokens of one specific example to a single expert or module. And this results in modules learning the similar concepts, not on the sentence or phrase level, but on the word level. So Lewis et al. Find that especially syntactically and semantically similar words are routed to the same modules. So we see here a set of words that are routed to the same expert, and we can see that words like US, UNESCO, and so on are routed to the expert 96. Metrics like years, billions, and so on are routed to expert 5. Then we have some entities routed to 43, and so on and so forth. So we can see that the model does learn somewhat modularity, but not on the sentence level or example level that we might be interested in from a modular perspective, but more on the word level. And we have to note that the main objective of these approaches of the switch transformer is not modularity, but actually efficient training of models. So they want to sparsely activate very wide layers, basically, and that does not necessarily mean that this is a bad idea. It is just a completely different objective, but unfortunately, just will never learn a modular component, at least not from the perspective that we're currently interested in. But that doesn't mean that these concepts cannot be used for in a similar sense. So, for example, if we utilize this general concept, but instead of routing on the token level, we can route on the example level. So, so basically, what we aim at doing now is relax this load balancing notion. And give the model the capacity to learn and to route all of the tokens of an example to a module, hoping that this would result in more modular components on the entire example level. And this can be done, for example, again, using this concept of passing through a task ID to the router, or pooling over the token representations, and then routing that to a single expert or module, which has been done in some of these papers down here. Now, the decision obviously does not have to be on the layer, but can also be on done more globally. So a router can make the decision at the start of training, for example, using the task ID, and then at every single layer, the same routing decision is made for the respective modules. So this is obviously a simple extension to all these concepts that we have talked about in the earlier part of this talk. And these concepts are obviously complementary, so it doesn't necessarily mean that we have to have a fixed routing across all scenarios, but we can combine, for example, fixed and learned routing. One example would be that we make a fixed routing decision on some type of metadata that we have available, such as the language information. So, for example, we often know what language a sentence is written in. So based on this information, based on this metadata, we can perform fixed routing and route the examples to the corresponding language-specific modules. But in order for us to disentangle more heterogeneous data, we can provide the model with the capacity to disentangle those concepts through learned routing additionally. So this can be, for example, training on unlabeled data on MC4, for example, where the model then has the capacity to disentangle similar concepts that are shared across languages. Okay, cool. So this was the section on routing. So we've talked about how the routing selects different modules during training. And now in this section, we're trying to understand how we can aggregate the modules in order to combine the information that we have stored within them. It's important to note here that this does not necessarily mean that these are concepts that are strictly disentangled from each other, because many methods actually perform the selection and the aggregation simultaneously. So for example, the mixture of expert scenario, we have the routing and the aggregation in one method integrated. So we're just, in this aggregation section, we're just trying to look at this concept from a different perspective. And also a additional reminder, in the first part of the talk, Sebastian talked about computation functions. So here the interesting concept that we looked at was how we can compose shared components with modular components. So we have the set of pre-trained weights, for example, and how do we compose these components with the modular components. And here we are interested in how we can compose multiple modular components. So not composing the shared with the modular components, but across modular components that, for example, we have trained on multiple different tasks. So looking at the notation part, we can always see that the initial way of formulating this was based on the shared and modular specific parameters. And now we're extending this to the modular composition framework. So while in parameter composition, we looked at how we can compose the shared weights with the modular specific weights. Now we're aiming at the parameter composition of multiple modular set of weights. Similar to the input composition, here we concatenated the input examples with, for example, prompts. Now we're extending this and continuously concatenating more prompts. In the function composition, we were interested in how we can compose the functions of the shared functions with the modular functions. And now we're interested in how we can compose the functions of multiple modular units. And from a more illustrative perspective, we have these modular components, and now we're trying to see how we can merge them to share the information that are stored within them. Okay, so first of all, let's look at parameter interpolation. Now, as you probably know, interpolating between weights is non-trivial. So imagine that we have Bert and Roberta. They are somewhat similar from their architecture. Now, if we would just say, if we would just average the weights of these two pre-trained models at each of the individual layers, then we do not assume that the resulting averaged version of that model will perform very well, because the dimensions do not align between these differently randomly initialized models. Now, in order for us to design an algorithm that where we can actually interpolate between these parameters, we have to look at mode connectivity. And mode connectivity is defined by a minima that is found between two models that are connected by a path of non-increasing error. So if we define a function that connects us between these two models, then they are mode connected if in this connection path the loss does not significantly increase at some specific point. And some previous work has actually found that linear mode connectivity, that means we want to interpolate between models in a linear fashion, so a direct interpolation between the weights, this is closely connected with the lottery ticket hypothesis, which Sebastian has talked about earlier. And specifically, what they have found is that if we have two models that are initialized with the same set of weights and then fine-tune on maybe two different tasks, then the models tend to stay in the same loss Bayesian when we interpolate between them. So this is illustrated by the plot on the right, where the purple, where the interpolation between the left model and the right model is done through a linear interpolation coefficient. And we can see that for the purple model, where both models are trained on different tasks, but they're initialized with the same set of weights. So yeah, it can be, for example, a pre-trained model such as BERT, and now we fine-tune it on NLI and on sentiment analysis, for example, and now we want to interpolate between those two weights, then we can see that the test accuracy does not drop significantly at any interpolation coefficient. So there is no barrier between those two models, even if we interpolate between the weights. On the other hand, if we have two models that are initialized with different weights, indicated by the blue and red models here, then the interpolation between those weights results in a sudden decrease in accuracy. And that is the loss barrier that exists between those two sets of models, where only close to the weights of the respective models we perform quite well. And as soon as we try to interpolate between them, we hit a loss barrier. And building on this concept that mode connectivity works especially well for, and linear mode connectivity works especially well for models that we've initialized with the same set of weights, are parameter interpolation methods that we can build on top of this. One of this being the lottery ticket sparse fine-tuning, with which Sebastian has talked about earlier already. And here, specific subnetworks are identified for different tasks. We are training sparse subnetworks for different tasks, and these subnetworks build on the same set of pre-trained weights. And because of this linear mode connectivity between these sparse subnetworks, we can actually perform arithmetic operations on them, meaning that we, for example, add language-specific subnetworks to task-specific subnetworks, and this results in a positive cross-lingual transfer, for example. Ilarco et al. Even proposed to edit entire models, so not only the sparse subnetworks, but learn basically these editing task embeddings, what they call them, on the entire model. So the example that we have here is that they start with a initialized weight, initialized model pre-trained on some MLM task, and then they train it on toxic language. And another model, another version of that model is trained on general language modeling. And so following that, they perform an arithmetic operation, subtracting kind of this toxic text subset from the original model and add the general language modeling objective, general language model. And this turns out to result in a model that still is very good at generating text. So it does not forget its original capabilities of generating text, but it suddenly has forgotten to generate toxic text. So they show that this significantly reduces the toxicity. And so you can perform this modular parameter interpolation by with very cool arithmetic operations because of this linear mode connectivity between models that is due to the models being initialized with the same set of weights. So second of all, we'll look at input composition. So input composition is, for example, prompt tuning or prefix tuning. And here the aggregation of these modular components comes actually quite natural, because we've already concatenated these modular components, such as a prompt, with the input. So there's no reason for us to do it any differently in order for us to aggregate these modules. And so for prompt tuning, this actually just boils down to concatenating all the prompts that we, for example, trained on different objectives. In other words, we just prepend more and more prompts to the text input. And one kind of illustrative example of that is the general way of how we perform few-shot learning. The more examples that we provide the model with in, for example, GPT-3, the more class labels it actually knows, and the more class labels the respective following text will actually be able to classify. So we can extend this kind of concept to more and more class labels by just extending the model with more prompts. In a similar fashion, the general idea can be extended to also to prefix tuning, where these additional prompts from trained on or prefixes trained on different tasks can just be concatenated in order for us to perform this composition of modular units. To the best of our knowledge, this has, however, not been evaluated yet. Okay, so finally, we'll look at function composition. And here we have a set of modular units like adapters or nonlinear functions that we need to select, and each of which produce a hidden representation. So if we have a set of F modules, then we receive HF hidden representations as an output of each of these modular units. And now the question is how we can aggregate those. So the idea is that by performing a forward pass through these modular components, the information stored within them will transform the representations in a way that this added information is now in the hidden representations. And the simplest way of doing that is learning a linear weight for each of these hidden representations, and then we can perform a weighted average where the weight is the learned alpha. And if we remember, this is closely related to the definition of mixture of experts, for example, where the alpha is learned by the router and the hidden representation is the output of each of the individual functions. So this specific example actually is the exact same formulation as in mixture of experts. So looking at this again, we get each of the router assigns a weight to each of the edges. We receive the hidden representation from each of these modular components, and then we perform a weighted average across these hidden representations. So essentially, MOEs perform routing and function aggregation automatically. Now, this idea has been extended by Ma et al., where they actually learn this aggregation or routing function per task for multitask setups. So, for example, they have this red task and this blue task, and even though the functions or these modular components are shared across tasks and the hidden output representations are the same, depending on the task, a different weighting can be assigned to the respective modules. So for example, the red module highly weights the second module, whereas the blue module for the blue task, the router selects a higher activation of the first module. And so different kind of aggregations of the hidden units can be realized respectively. An alternative way of function of weighted representation averaging is, for example, in demixed layers proposed by Gurungan et al. And they learn a posterior distribution over domains. So what they do is they learn, they pre-train modular components on different domains, such as health data and use data. And now if they receive an input example of a domain that they either don't know the domain of, or that has just not existed during pre-training, then they utilize the posterior distribution, which they calculate using a Bayes theorem to learn to define a dynamic weighting over the existing modules in the network. So for example, if they have a COVID-19 input example, then the posterior distribution over this input example identifies that this is a combination of health and news data. And so they aggregate over these two output module representations accordingly. Now, all these concepts can also be extended in many different ways. In fixed routing, there are approaches that have proposed to average, just perform normal averaging over the representations. This has also been done in hard learned routing, for example, in Polytropon. But we can also just sum over all the output representations directly with no averaging, which has, for example, been done by PathNet. Now, the problem with these scenarios of weighted representation averaging is that the decision is made before we actually make a transformation of the representations. So that means we don't actually know what type of information has been added to the representations. So alternatively, what we can do is attention-based representation aggregation. So here, the idea is to first do the transformation and then identify whether or not the added information is actually useful. So for example, if we have 3 modules available, we can learn an attention mechanism where the input to each of the modules is interpreted as the query, and the output of each of the modules is interpreted as value and key. So the dot product between key and query, followed by a softmax activation, learns to dynamically identify which module has added useful information for the respective downstream task that we are interested in. And we have a dynamic weighting of the corresponding representations at every single layer. So here we make the decision after we've performed the transformation. The problem with both this preemptive selection and post-emptive selection is that actually we require a full forward pass through all the modules. That is the case even if these modules do not contribute to the final representations at all, because the activation, so the selection of those modules, is actually very low. So in that case, in hindsight, we know that we would not have had to do a forward pass at all. And so this significantly increases the time and space complexity of the entire scenario. Now, we can mitigate that slightly through pruning or kind of dropping out modules during inference, but still, like, this latency issue is still existent for all these approaches. An alternative direction of how we can compose function is a sequential aggregation. And that means we take the output of one module as an input to the next module, so we can sequentially pass our representations through multiple modules. This has, for example, been done for cross-lingual transfer, which we will talk about a bit more later, where we can add more and more information specifically to whatever we're training on. So this can be, for example, task information, language information, domain information, and so on and so forth. So we sequentially add and make transformations on the hidden representations, depending on the functions that we're passing through. Now, all of these concepts are complementary, and even though we talked about them from a very kind of distinct kind of perspective, that doesn't mean that they cannot be combined. So we tried to kind of provide you with a rough overview of computation functions, so how we can define modularity, how we can route to these different modular components, and finally, how we can compose and combine the information of all these modular components. And in the next section, we will actually look at some case studies and applications of methods that have successfully used individual subcomponents of what we've discussed in the first part of this talk for different transfer scenarios. And for this, I will hand over to Ivan. Thank you.
Hello, good morning, good afternoon, good.
Thanks so much, Jonas. Just quickly, I think we do have time for maybe like 1 or 2 questions for this section, if anyone has any here in the audience. Cool. All right. Yeah. If not, then we can also jump to the next part and just take questions. Oh, okay. Cool. Test. Yeah.
You know, from a lot of this has to do, I think, with like lower computational power. Basically, we're trying to train with lower computation. Is there like particular cases where you would select choices here based on having less data, right? Lower resources, right? Like fine tuning with not a lot of available data. That's my question, I guess.
Was that clear, Jonas? Did you hear that?
Yeah. So is this which part is this question specifically for? Like, is it the aggregation or the routing? I think depending on what scenario you're interested in, we have different answers for that, I guess.
Well, all of the above, I suppose, right? Like
yeah,
Swahili or something, just some small amount of Swahili data. I want to fine tune some large language model efficiently, right?
Mm-hmm.
But I don't have a lot of data for it.
Yeah, I mean, if you already know that the training data is in Swahili, then the routing decision, for example, is probably a bit easier because you do know that it's Swahili information, right? So in that specific case, you can perform fixed routing in the sense that you perform the routing, you know, based on the metadata that you have available, and then you then I guess the question is how much available training data you have in Swahili for as training data. If you do not have any training data available, then you can try to utilize other data sets that you might have in different languages and disentangle, you know, task from language information and perform routing on that level. Yeah, like it really depends on the specific scenario, how aggregation can be performed. I think that some of these scenarios are going to be addressed in specifically the applications section right now. But if you're just interested in parameter efficiency perspectives, then different approaches from the first part of the talk might be applicable, where some of them are maybe more parameter efficient or less susceptible to overfitting. I don't know, like.
Thank you.
Yeah.
Yeah. All right. Yeah. And if you have any specific questions on particular scenarios that you are interested in, you can also write them in the Rocket chat, and we can get those individually. Cool. We have, I think, maybe one more question in the Zoom chat here. Does backpropagation for top K routing work differently than for hard-learned routing?
Yeah. So with top K routing, we can just backprop through that because we have a continuous selection, and in hard-learned routing we make the decision is specifically, you know, a categorical distribution, and so we cannot actually backprop through this categorical distributions, and so we need to reformulate the problem, for example, through policy gradients or other stochastic group parameterization tricks. So it's not as easy as backpropping through, you know, a top K routing scenario. So top K routing is just vanilla gradient descent, and hard-learned routing has to be done with some other version of learning.
Yeah, thanks. So, but we are doing top 1 routing, as in essentially we are doing something like some kind of argmax or even the top K, and we have to zero out like modules, right?
Yeah, so top 1 routing is basically a very specific case of that, where we can backprop through it, but it usually would result in module collapse if it's just a top 1 routing that we do, and the way that the switch transformer specifically learns top 1 routing is through massive amounts of data and additionally this load balancing. And this load balancing introduces stochasticity in the formulation, whereas if you do this in its vanilla implementation, it probably would not work.
Cool.
Okay.
And, thank you. And last question, how should people evaluate routing or their routing approach? Is there a benchmark that they can use?
Very good question. It's very, very difficult to define that. And I don't think there is any good way of evaluating that right now. And it's really an interesting research question that I think is very important to address in the future.
Cool. All right. Thank you, Jonas. Okay. Yeah. With that, we can give it over to Ivan, who's going to cover applications now.
Thank you. So yeah, Sebastian and Jonas did all the heavy lifting. So they introduced everything, defined everything, explained everything. So the last part of the tutorial would be just putting all these things in practice, and basically I'll go through like a very non-exhaustive subset of applications, but we've seen those usages of parameter efficient and modular approaches, mostly in NLP, but I'll also draw some connections to other areas of research like computer vision and speech processing. And yeah, but again, we'll start lightly. So first, I mean, why people started investigating all these parameter efficient and modular fine-tuning was first to actually deal with limited computational budget. So we wanted to actually bypass tuning of the full model, but the modular perspective is we also wanted to avoid negative impact of sequential fine-tuning for for example, when we actually learn parameters for one task, but when we want to learn another task, then of course we copy over the previous parameters, etc., etc. If we do multitask learning, the different tasks compete for the same fixed parameter budget, which then leads to catastrophic interference. And if we actually have dedicated modules for every single task, these things can be prevented. So this was one of the high level ideas. But let's not talk only about the negatives here. As we said, part of the work is also to boost efficiency, because if we have smaller dedicated modules, then we don't have to fine-tune the whole model, which actually leads to better time efficiency of training. We can create more compact models when they're getting fine-tuned, but there are also positive aspects. So positive aspects are enabling positive transfer, which means that similar functions can actually be encoded within similar modules. So we can actually reduce data scarcity. So for example, if we're dealing with very similar languages, we might actually create modules that cover like a set of languages, not only a single language, so that we can learn some interactions between similar languages. Another important aspect of modular design is compositionality and reusability, which is something that we already touched in this tutorial, which actually leads to systematic generalization. And what it means is basically that we can create modules to do like to cover tasks X and Y, and even without ever seeing how X and Y are dealt with in combination, we can combine dedicated modules and actually generalize towards performing X and Y at the same time. So think of maybe like very simple skills, like if we know how to go right and how to go up, we can then like combine going up and going right using dedicated modules that actually tell the system to go right and up. This is like a very blatant example. Another important aspect is, of course, parameter efficiency, which is what we already talked a lot about, where we can actually perform these like local asynchronous updates, and then after the local updates, we can actually aggregate the models. So this is all the routing and aggregation parts that Jonas talked about. And another important aspect is also scaling, which is typically done, for example, through a mixture of experts, where we can create those specialized modules that can perform special functions that actually sit within like a large network, and then we can activate different parts of the network based on what we are processing at the moment. So this is again related to routing, etc. So we will focus on some applications. We'll go in depth for low resource multilingual cross-lingual NLP. We worked a lot in that area, so we know the area well, and I think it also lends itself really to illustrate some of the core concepts that we defined before. So when we talk about parameter efficient fine-tuning, I think like a basic scenario, which is typically how it is used across many applications, is okay, we have our large neural model, which is the base model, and we just want to perform a specific task. So you can think about like standard glue style, super glue style tasks. You can think about like other tasks as well. But the idea is then to have this dedicated module, which could be defined as an adapter, as a prefix, tuning, instantiation, etc. And we want to store all the task relevant knowledge within that task specific module without actually doing any updates to the big large model. So all the updates when we are doing task fine tuning are forced into that task specific module. So we can call that a task module. And then typically what people do in evaluation is that we compare against full model fine-tuning and other parameter efficient approaches, typically on a standard benchmark like glue or super glue. And basically then it also depends which benefits you want to reap from those task specific modules. So people have either focused to improve performance using the same limited parameter budget, or another win that you can strike in this basic setup is maintain performance, but using a smaller parameter budget. So you're trying to create as efficient modules as possible, or maybe you're trying to boost sample efficiency and maintaining performance with that. So this is sort of a basic scenario. So but this basic scenario again treats every single task in isolation. So we can create like a task module for task one, a task module number two for task two, etc. But those tasks do not interact. So here, like, positive transfer is limited. So one approach that already made a step forward, and beyond that basic approach, is the work from Mahabari et al., which actually used hypernetworks, which you also saw in the previous parts of the tutorial, to do task conditioned creation of these modules, which means that we can actually capture the similarity of the tasks through task embeddings, and so that we can also like share knowledge between different tasks and create those task modules via hypernetworks that also are conditioned on this shared knowledge. So this is going one step beyond having like a completely isolated task module for each task. So we through the use of hypernetworks, we are allowing sharing between different tasks. So this idea will be exploited multiple times in this overview of applications as well. So but now after that, we're moving to cross-lingual transfer. As I said, it's a pretty interesting area for the modular approaches, because first, like beyond NLP tasks, which actually some of the tasks share like common knowledge, they need similar annotations, etc. So many languages also share a lot of structure, a lot of lexica, a lot of semantics. So on all these levels of lexical, syntactic, and semantic processing. And so this is again like one extra layer that we can add in cross-lingual transfer. And the problem with multilingual NLP, as you know, is that getting annotated data is very expensive. So we can't really annotate data for every single language out of 7,000 languages. So we have a lot of NLP tasks to deal with. We also have a lot of text data domains. So basically, if we are to do supervised learning in this 3D coordinate system here, we would actually have to annotate data for every single data point. So the question then is, if we can actually focus on domains only, on tasks only, and languages only, can we create a modular design which actually enables us to present each data point in this coordinate system by a combination of dedicated modules, which actually leads to systematic generalization. So this is again what I talked about before. So if we have a module that covers tasks, if we have a module that covers a language, and a module that covers a domain, we can actually create, we can aggregate or combine those modules to actually process a particular domain for a particular task in a particular language. So this is one of the main ideas of the modular design, and we'll see some of those ideas in practice for cross-lingual learning. Okay, so going back to cross-lingual transfer, which will be our first case study. So the typical approach to do cross-lingual transfer in modern NLP, and also before the days of BERT and PALS, was pretty much the same. So step number one is to train a massively multilingual model. So you can think about multilingual BERT or XLMR or MT5. So basically, step one means let's create a shared cross-lingual representation space so that we can actually do operations in source language in one language, and then do inference in another language. And we need a connection to that representation space. So step one is pre-training on concatenated multilingual texts, similar to what, for example, XLMR is doing by training on concatenated common crawl data in 100 plus languages. And so we have this multilingual representation model, multilingual encoder. In step two, we are fine-tuning the model on a specific task in a high-resource language, and then basically we're just taking the model fine-tuned on the task data from the source language to the target language. So we are just doing inference in the target language, because the main assumption is, again, this shared cross-lingual space. And the reason for doing zero-shot cross-lingual transfer is, again, what I said before: training data is expensive to create, not available for many languages. So basically, we are trying to bypass the data bottleneck problem. Okay, this is the standard cross-lingual transfer. It has nothing to do with modular parameter efficient design. So yeah, so those actually those approaches work pretty well. So if you do full model fine-tuning and then do zero-shot cross-lingual transfer, you will get state-of-the-art results with big models. But the problem is that they do not provide equally good representations for many languages and suffer from something which is called the curse of multilinguality, which is basically an instance of catastrophic interference, because we are trying to distribute the fixed limited parameter budget of those big models to many languages. From another perspective, we are trying to cram like all the knowledge from all the languages into that limited set of parameters that we have. So the curse of multilinguality actually means that as we keep adding languages into the mix, what we observe is actually degradation of performance even for high resource languages, because more and more parameter budget is getting dedicated to other languages. So even the highest resource ones actually start suffering if we are above a certain point. So basically this curve here shows that especially for lower resource languages, multilinguality actually does help. So having more languages in the mix enables positive transfer, so they learn from high resource languages, but at a certain point, the degradation happens because of catastrophic interference. And yeah, this is again happening for basically both low resource and high resource languages. So this is already like a call, an alarm for a more modular design that can somehow tell the model to specialize for a particular language. So basically how to combine the benefits of multilinguality that enables positive transfer and also the benefits of specialization for particular languages or particular transfer directions, etc. Okay, so we talked already about task modules, or like we'll use adapters for most part as like an easy instance to comprehend what is going on. So we talked about task adapters, but can we also learn what we call language adapters, which were basically we will try to store general purpose language information into these adapters, which basically means doing the same thing as pre-training a multilingual model, but just again forcing all the updates for a specific language to go to a dedicated set of parameters, which we will call language adapters. And basically, those language adapters could then skew the model in a good way from like a general multilingual model to that particular language if we are doing processing of instances in that particular language. So the task in this particular scenario is not like any task with supervised data, but it's again like a standard masked language modeling task that is operating on that particular language. So using, for example, masked language modeling, we can learn those language specific transformations, which actually do those transformations for English, Quechua, or any other language that you have already represented in the big models. So basically, through doing dedicated MLMing on English or Quechua, we can learn those dedicated language adapters. And yeah, so the actual forward pass goes not only through the big shared multilingual model, but it also goes through the dedicated language adapter when we are processing data from that language. And one assumption is that those transformations can be roughly interchangeable if the extra language specific training for language adapters is done on the data of similar domains. So for example, what we often do is just train on the full Wikipedia of the language. So this is a pretty strong assumption, but let's just assume that it holds in practice more or less. So this kind of enables to replace one language adapter with the other language adapter within the whole structure of the big model. Okay, so this is a pretty important assumption. And so we'll delve deeper now into the adapter-based or modular cross-lingual transfer enabled by those adapters. where we can combine dedicated language adapters trained by masked language modeling with actually a dedicated language agnostic task adapters, which are trying to capture task knowledge. So for example, you can create a named entity recognition adapter, you can create a summarization adapter, etc., etc. So this is the main idea behind MEDX, which is an acronym of multilingual modeling based on adapters or something like that, or multiple adapters for cross-lingual transfer. I think that's the right thing. Okay, so the idea is exactly the same as in the basic cross-lingual transfer scenario. It's just that first we have to, in step 0 now, we already pre-trained our massively multilingual model. And now we need to create language adapters for the languages we actually care about, which means that we have to continue doing masked language modeling on Wikipedias of particular languages. So yeah, so this is done in step 1, which is basically improving our representation space so that we reap the benefits of cross-lingual representations combined with the benefits of specialized language dedicated representations captured in the adapters. This is what we do in step 1. So step 2 is training a task adapter. So yeah, in step 1, we freeze the entire base model. This goes without saying. In step 2, we are freezing the base model, but we are also freezing the language adapters. So we pass the information to the language adapters, which are, and we use source language adapters at task fine-tuning, because the assumption is that our task data is actually given in the source language because we're doing transfers. So think about, I don't know, transfer for named entity recognition. So we have only annotated data in English and we want to do the transfers. So what we're going to do is we're going to put our English adapter into the structure, pass the information to the English adapter, and then put a dedicated NER task adapter on top of the English adapters so that we actually do multilingual processing via the base model, English-oriented processing via the English adapter, and then learn supposedly language agnostic knowledge and store it in the named entity recognition adapter. So this is the main idea of training those task adapters. So everything else is frozen. We're just updating the weights of the named entity recognition adapter. Okay, and step 3 is again doing the actual zero-shot transfer, which is, okay, we now have to do transfer to the target language, for which we have seen 0 annotated instances. So you already see where this is going. So because the assumption is that language adapters are roughly interchangeable, we can just replace the source language adapter with the target language adapter while keeping the language agnostic task adapter, which actually gives us task specific knowledge. So when we do inference in Quechuan, we can just pass the language information of the data instance from Quechuan through the Quechuan adapter, and then use the NER adapter that we trained in English on top of the now Quechuan adapter. And this enables cross-lingual transfer. So this is the basic idea. And basically in this example, you've seen some instances of function composition and also like how we decide on routing and also like a very simple example of aggregation. So we are actually stacking task adapters on top of language adapters. Okay, so just a few numbers. So basically, cross-lingual transfer is meant to help low-resource languages to boost their task performance. So in the paper, we did cross-lingual transfer from 4 high-resource languages to 17 low-resource languages. And so, yeah, some of them were seen by the base model, and some of them were like completely unseen by the base model. So Mbert and XLMR, they just cover around 100 languages. And we also had some languages where even their scripts were not covered by the model. So and then we did a bunch of different subgroup analysis based on these different subgroups of languages in the evaluation. Yeah, so we had those 5 languages with unseen script, and And the results were quite interesting. So there's like a lot of red squares in this particular grid of results. But the important thing is that cross-single transfer typically deals with transferring from high resource to low resource languages. So basically, the only quadrant that really matters is the one highlighted here, which is really transferring from those like especially like the four high resource languages like English, Japanese, Chinese, and Arabic to those very low resource languages. And this is where we actually were striking most performance benefits. So like a long story short, it seems that like modular transfer between high resource and low resource languages is really possible without actually creating that interference effect or the curse of multilinguality. Yeah, of course, the results across different groups of languages were quite different. So languages which were seen by the model, actually we just stroke really marginal improvements, but it also worked slightly better. For unseen languages with seen scripts, we actually saw pretty good improvements for those low resource languages. And the problematic ones, the most difficult ones are of course the languages which are unseen by the model, and we even haven't seen like the script, which means that we couldn't really do tokenization correctly, etc. So the model really suffers for those languages. So what if scripts have never been seen? So I'll just skim through that work. So for example, one language that didn't have script seen by Mbert is Amharic, and this is the script of Amharic. And basically what happens if Mbert tokenizes Amharic text is you just get a bunch of unks, so you don't know how can you deal with those unks. And the idea is basically to learn to extend the new tokenizer in a modular way again, because we now have like our adapters, our modules, which are dedicated to particular languages. So when we are doing the extension to unseen scripts, we can actually copy words that are seen also when we in Amharic to the Amharic dedicated tokenizer, and then continue learning a specialized tokenizer for Amharic. So in the paper from Jonas and other people, EMNLP 2021, we actually provide a bunch of different methods that can help you extend those tokenizers to unseen languages and unseen scripts, and this leads to massive improvements. I'm not going to go into detail. So I mean, most of the application coverage will just try to address like very high level ideas that are hidden within all those papers that we cite. And yeah, so we do copying, and then we do updating of the actual tokenizer and the embedding matrix, so that we can process the unseen language and the unseen script more correctly. So that's like an extension of the basic MEDEX setup, and this really helps with unseen scripts, as you can see from the graph here. Okay. So this was again, like if you remember the basic scenario, we just randomly initialized adapter module parameters in isolation for languages and tasks, and then we actually created those language adapters in isolation. So again, there was no real positive transfer between the very related languages. So the idea is again to use hypernetworks to generate parameters of language adapters or language models now, which are now conditioned on language representation. So you can think about language vectors, which can come from different typological databases, or and then you're trying basically to factorize adapter parameters into language and potential layer-specific parameters. So you can insert those adapters or modules into every single layer of the network. So you can also condition the generation on the particular position in which you're inserting those. And this is not only enabling positive transfer, this could be also more efficient than keeping dedicated language adapters, because we actually, what we have to store as parameters is basically just the generator hypernetwork that creates those those multiple language adapters on the fly when they're conditioned on a particular language. And in theory, it could work in completely zero-shot scenarios. So you can imagine like a very wild, extreme scenario where you don't even have any text data for a particular language, but you can get its language vector, its language representation from some typological database. So you can generate the language adapter for that language just conditioned on the language information that you have. Or if that language has like a closely related sibling, even if we don't have any text data for that language, we might have some text data for its siblings. So it will actually require very similar language adapter to process that. So this is like a very extreme scenario, but in theory, this setup with hypernetworks enables it. So this is exactly the idea of the extension of MADX, which is called MADG, where G stands for generation. So the idea is exactly what I just said before. So we are trying to learn to generate a monolithic multilingual adapter by doing mass language modeling on like almost 100 languages. So we know the language of the example. And so what we are actually training is the hypernetwork that gives us the actual generated language adapter for the particular language conditioned on the particular language vectors. So that way we can actually generate the module on the fly. So if we see the input comes from Swahili, we will actually condition generation on the Swahili vector. If we see that the input comes from German, we'll do it condition on the German representation. So this also enables like a very natural multi-source transfer. So if we have annotated data in more than one source language, we can actually easily combine the generation of language adapters on the fly with the use of a multi-source task adapter, which is stacked on top of the generated language adapters. So another benefit of this approach is that the generated adapters might actually give better initialization for further target-specific mass language modeling than just doing a completely random initialization of the new adapters. So if you want to extend our model to an unseen language, it's probably better to start from a multilingual adapter which has already some inductive bias towards learning natural languages than starting from a completely random distribution of the parameters for that new language. So this is the idea. So again, this creates more efficient and more compact designs. So for example, I wanted to put this slide just to basically see how parameter efficient we are getting. So imagine that you want to create specialized embed copies for each of the 95 languages. If you're doing that, you will need almost like 17 billion parameters for 95 languages. Having MADX requires around 700 million additional parameters to actually capture like 95 single language adapters. I don't really know what reduction factors we are talking about. So I think this is with the reduction factor of 2, but yeah. If we're doing the MADG approach with hypernetworks, which is conditioned only on language vectors and not layers, we actually, for the same number of languages, we need 3 times less parameters. And if we're also doing the factorization over language vectors and layers, which means that both affect the actual generation process, we can further bring it down. So by the number of layers in which we're doing the actual conditioning. So this boils down to having only 38 million additional parameters to actually do specialization of a massively multilingual model like Embed to 95 additional languages. And something that's also pretty important is per language training time. So what we did in the paper is we actually let the MADG training run 50 times shorter than the time that would be needed to actually learn language adapters for all the 95 languages, which is also like a massive benefit in time efficiency of training. And it doesn't even work so bad, to be honest. It actually works really well. So we are presenting here just 2 basic results. One is on the NER task on the Masakane NER dataset for African languages, where MADG actually even like massively outperforms full model fine-tuning XLMR and MBERT by a pretty huge margin. So really, we could see the benefits of the positive transfer happening and the modular design, especially for low resource languages again. And this figure here is again to illustrate what I just mentioned before, the fact that we can initialize a language adapter from that MED-G multilingual adapter instead of doing random initialization, which really helps for low resource scenarios where we just have like a small number of even annotated text data for the particular low resource language. So think about just having the Bible or some other like religious text in that language. So that's the only data that is in the written form for the language. So it even helps with the tasks like dependency parsing to start from the non-randomly initialized adapter. Okay, so another step beyond MED-G is HyperX, which actually combines conditioning of those hypernetworks to generate modules not only on language and layer, but it also adds task in the mix, which means that this hypernetwork then also can support unseen task language, and it also learns from the positive transfer between tasks. So conditioning only on language and the layers enable positive transfer between different languages, but additionally conditioning on tasks enables positive transfer between tasks and languages. And it actually, it adds even more information to the generator network, which then can help to the model to deal with data scarcity problems at the level of languages and tasks as well. So that's the main idea behind HyperX. Again, I'm not going to delve deeper into the paper because we just don't have time for that. Okay, so all of this was done at the level of fine-tuning. So the assumption was, okay, we already have a pre-trained massively multilingual model, so we are trying to specialize it for particular use cases, where use cases could be particular languages, particular tasks, or the combination of tasks or combination of languages. But what we can do is also modularize those language models from the scratch, from the very beginning, which means that we can already reserve some like dedicated parts for particular purposes, in this case, particular languages from the very beginning of training. And this is exactly what XMod model is doing. It's basically, it can be seen as MEDX at pre-training. So as we discussed, MEDX is, okay, pre-train first a massively multilingual model, and then insert dedicated language-specific modules in the pre-trained model. What XMod is doing, okay, we're going to reserve these small blue and green boxes per each language, these modules per each language already at the start, and basically, what we can do now, if we want to extend it to another language, we have those dedicated parts in the previous N languages, and plus first language will get its own set of dedicated parameters, and we can continue pre-training just using that particular language, which actually gives us both like reusability of the previous model and composability with because we can keep adding languages into the model. And so you can actually have a shared baseline is a standard multilingual model with all weights shared, and XMod is where each language has a set of dedicated modular parameters. So we are combining that or leveraging that old idea of combining shared and non-shared parts of the model. And again, as I said, XMod is basically a MEDX for pre-training. So again, like each language gets its own dedicated language adapter at pre-training. And zero-shot cross-lingual transfer with XMod is pretty much the same as before. So when you do fine-tuning for a particular task, you're just going to fine-tune the shared parameter. You're just going to fine-tune the shared parameters, and then at cross-lingual transfer, you will replace the source language module with the target language module as done before, because those modules actually store language-specific knowledge. So that's the main idea. Okay, we now something slightly different. So we talked a bit for most part, just only about adapters, but other modular designs can also be used for efficient cross-single transfers. So, for example, sparse subnetworks could also be used for the same purpose, where the idea is pretty much the same. So if we think again in terms of MEDEX style transfer, we have a large multilingual model, and then we are trying to find sparse subnetworks that actually store specific language information, and also sparse subnetworks that store specific task information. And then we can combine those sparse networks because we are trying to leverage sparsity, like over-parameterization of the model. And then we can combine language-specific information and task-specific information, which basically means combining language masks and task masks and append them on the base parameters of the base model. And this could actually give us a model specialized for a particular language or a particular task. It means that, if we apply a language mask first, and then we do task fine-tuning with the source language mask, we can learn that language agnostic task mask, and then when we do inference, we replace the source language mask with the target language mask and apply the same task mask to do the transfer. That's the main idea. As you see, there's like a really tight connection with the MEDEX style transfer. Now, there are like different ways how to choose which subset of parameters should go into those language and task masks. So you've already heard about the lottery ticket selection procedure, which is one of the ideas. And there's like a whole body of work on extracting those subnetworks, typically in monolingual scenarios. And we can apply similar principles here. So there is work which tries to do approximation of the Fisher information matrix to actually choose which parameters might actually have the most impact on the final behavior of the model. So you're actually then selecting only the top K parameters with the highest value for a specific criterion that you define. It could be the magnitude of change, it could be the Fisher information. So this is the main idea. And again, sparsity is crucial here. So these graphs here basically show that the highest performance, which are the brightest colors, is actually, we strike highest performance at certain levels of sparsity. So if we create denser and denser subnetworks, they will actually start colliding with each other. So we actually go into the interference zone again, and this will prevent the modularity principles to happen in the actual transfer, which will actually have negative impact on performance. So again, how to strike the optimal sweet spot level of sparsity. This is again like an ongoing research question. A similar principle was also applied in the work of Vulić et al., which is published at this year's EMNLP, where instead of combining language and task masks as separate entities in a sense, so they were combining language and task information into a single mask. So this again, the granularity depends on what you're trying to optimize, whether you're trying to optimize modularity, parameter efficiency, or the actual performance of the work. Again, this is an example where exactly the same idea was applied for information search in multilingual cross-lingual setups. So the idea here the task is basically ranking. So it's not NER anymore, it's or parsing. So this is one application, information retrieval, where you're combining ranking masks again with language masks, where the ranking mask or the ranking adapter is fine-tuned on the relevance assessments which are available only in a single language, which is typically English. And then you can transfer relevance assessments from the source language to the target language and do information search in the target language like Italian, Finnish, Croatian, Chinese, whatever. And this also enables multilingual information search, where basically you don't care about the language of the query, about the language of the document. If you have those languages supported within your multilingual model and within your modules, you can actually type a query in one language and do search of documents in another language. So this is exactly the same idea as with standard NLP tasks, but the application is in more towards the IR side. Okay. So we can extend modular cross-lingual transfer even more. So people were quite creative in how they actually design those adapters. So again, to boost positive transfer across closely related languages, we can even learn those modules not at the level of single languages, but at the level of linguistically informed groups, like phylogeny-based hierarchical adapters, where we can learn adapter for Romance languages, adapter for Germanic languages. We can learn an adapter for the group of Indo-European languages, and we can again stack them in a hierarchical fashion and then aggregate their outputs in a way we see fit using some of the aggregation methods that we mentioned. So this was done in a very recent paper as well. Another idea is also doing some sort of ensembling at test time where, okay, what happens if we have a low resource language? We have a bunch of language adapters trained for other languages, and then we're trying to mix and combine them and get better performance for that low resource unseen language. So we can try out different strategies, like just using a language adapter from a related language. This works to a certain extent, or we can average outputs of multiple related adapters where we again select them based on some criteria of language proximity, or we can do something even smarter. So basically learning weighting of adapters at the sentence level via this method called entropy minimize ensemble, which is a paper from last year's EMNLP. Again, this is like a very high level idea. I'm not going to go into the details of the actual procedure. And so this was all about cross-lingual transfer. So similar ideas have also been explored in the NMT community. As you can see, there are like direct connections. So basically, the only difference is that in cross-lingual transfer, we're kind of dealing with multiple tasks that we are trying to transfer across the board, and NMT is more or less dealing with a single task, which is translation. But all the principles remain exactly the same. So in this seminal work from Bapna and Vulić, so what they were trying to do is, again, they realized that this curse of multilinguality is happening with a massively multilingual NLP model. So they were trying to give extra capacity to particular language pairs, language directions, so that they can restore the performance for high resource language pairs and still reap the benefits of positive transfer across different languages in a massively multilingual model. So yeah, so what you're doing is basically you're starting from a multilingual model, and then you're specializing it to a bilingual model, but it's much better than doing it from scratch. So this, because you are still enabled positive transfer between all these like high resource and low resource languages. So what I actually did was just using bilingual adapters for skewing the multilingual model towards a particular translation direction. The same idea was applied by Vulić et al. For cross-lingual transfer, where like BEDX is basically a version of MEDX with bilingual adapters, where the idea is to boost transfer for a particular transfer direction. So there is a trade-off between higher modularity and higher performance. So what was done in the work of Vulić et al. Was basically, if we care only about transferring from English to Swahili, let's combine English and Swahili data into a language pair adapter, because that way we can, the task adapter will actually get adapted both to English and Swahili, because in the MEDX scenario, we just did zero-shot transfer. So the task adapter never saw a single instance of a Swahili and annotated data. So it was unfit to do like inference in Swahili in a sense. So we are better preparing it for the target language by doing that. Again, going back to the connections between NMT and cross-lingual transfer, then since Bapna and Vulić designed bilingual adapters, they actually required adapters for every single language pair, and so which means like lower modularity. So follow-up works of Philip et al. And Ustun et al. Actually created monolingual adapters for neural machine translation, so that each adapter actually just covers a single language. So we need like a monolingual adapter in the encoder side and the one language adapter on the decoder side. And you can already see how this enables, this power module design actually enables recombining adapters to boost even unseen translation directions. So if we actually have if we have a good language adapter, English language adapter in the encoder, and we have a Swahili adapter in the decoder, even without ever seeing like English Swahili parallel data, we can combine English and Swahili within the network to enable translation from English to Swahili. So so this was done especially in the work of Ustun et al, where they were actually they introduced monolingual adapters for neural machine translation, which are based only on monolingual data training. So they don't even require parallel data in many of language pairs. So they still require parallel data to actually learn the interactions between encoder and decoder and cross attention, etc. But the model can generalize to unseen connections. So again, a connection to cross-signal transfer is also through the use of hypernetworks. So very recent work from Baziotis et al. Instead of using initialized modules from scratch, we can actually again do generation of those modules. So they just did what MedG and HyperX actually did in cross-signal transfer, just for NMT. So they are doing those using those hypernetworks to generate adapters in the encoder and decoder part of the NMT model, again leveraging positive transfer. And here are some results showing that we can actually strike similar performance or slightly better performance with hyperadapters with the same or even smaller parameter budget. So this again goes back to the main goal of your application, whether you want to improve performance while keeping the same parameter budget, or you want to further reduce the parameter budget and try to maintain or slightly improve the performance. Okay, so again, adapters are not the only module that was used in NMT. So people have also tried to learn language-specific subnetworks from multilingual NMT, which is really similar to the work of Ansel et al. That you saw before on sparse subnetworks for cross-signal transfer. Again, the idea is the same: avoid interference and create specialized subnetworks for particular languages or language pairs, where sparsity is again the key. And this is something that Jonas mentioned. So a mixture of experts models was used to scale a multilingual NMT to really large models, where the key at inference is whether to actually do routing at token level or task level, and task level actually creates more efficient inference because each sentence is actually routed to a single expert. So we are not routing every single token to every single expert, which means like loading every single expert and then computing it per token. So this is more like an efficiency benefit of task level routing for a mixture of experts in NMT. And very similar ideas have been explored for the main adaptation. Again, we can deal with languages, we can deal with tasks, but we can also deal with different domains. So you remember that work that actually did like a hierarchy of languages. So we can apply pretty much the same idea for a hierarchy of domains and then learn dedicated adapters at every single layer of hierarchy, and then combine the knowledge to do domain adaptations. So domain modules can be also combined with language models and task modules to have a complete this entanglement between language, task, domain-specific information. So now, like I think I will have to finish very quickly. So what we have, and this will be left unsaid, a few more applications slide by slide in many other different areas of NLP and beyond, just to basically show the same principles, and that it can be used for, I don't know, continual learning, for task-oriented dialogue systems, for example. We can replace prompt tuning methods with actually modular adapter-based methods for few-shot learning. And there's like a really nice paper from Mahabadi et al, which actually shows that we can strike so many benefits by just resorting to adapter modules instead of doing prompt fine-tuning for few-shot learning. So again, not getting into details. Modular design is also very useful for multimodal learning. So we just have like a few case studies here. So for this particular example is basically doing prefix tuning, where your prefix is actually the flattened vector of a visual representation. So you're trying to actually generate an image caption where you're generating it conditioned on the prefix, which is exactly, yeah, as I said, a flattened vector here, and then you are fine-tuning again only the adapter blocks within a big generator model. So that's a pretty neat idea of doing prefix tuning on visually conditioned information. Or you can use the modular design also to extend monolingual monolingual multimodal models to deal with more languages, or you can actually extend a text-only multilingual model like Ember to deal with another modality like vision. So this can also be done via dedicated modules that process dedicated modalities. You can combine modules with sentence encoder to actually provide better representation power for particular domains or particular tasks. So you can even insert like knowledge that comes from contrastive fine-tuning into those adapters. So this was also done in for task-oriented dialogue systems. You can also do composition of prompts. So you can do modular prompting. So there's like a very interesting paper at this year's EMNLP, which actually combines like a language-specific sub-prefix with a task-specific sub-prefix. So you can then boost novel unseen combinations, which is again the instance of usability and composability that is enabled by the modular design. So yeah, that's another work, and similar principles have been used in other areas. So we have one example from speech processing. It's just that the actual objective function is different, the actual base model is different. So we are combining the CTC loss with weight to back model in speech processing. For example, if you want to do ASR, but you're still using exactly the same high-level principles where you're trying to force a particular knowledge about languages, demographics, like accents or kids speaking, domain-specific speakers into dedicated modules so that you don't really get into the problems with interference, forgetting, so that you also equip low-resource scenarios with more dedicated modules as well. And yeah, here's a list of other multiple application areas, et cetera, and just a quick reminder that community-driven initiatives can be seen as ever-evolving multitask modules whose modules and creation of those components are distributed throughout the community. So we hope to see similar initiatives also in computer vision, and maybe to have like a dedicated adapter hub for speech modules as well, and go beyond adapters. And yeah, so this is something we already talked about. So what can be stored in the modules? We typically talked only about language information, task information, domain information, but we can also store external knowledge into those modules that come from manually created databases. So people have tried to do that. So we already talked also about storing some debiasing related information so that you can actually do even intersection debiasing. So imagine a scenario where actually different knowledge about different biases is captured in different modules. So we can then stack all these different modules together and then do intersectional debiasing without hurting model performance, because everything is actually kept apart from the base model. And very recent work also goes beyond well-formed interpretable units of knowledge like language domains and tasks into an inventory of so-called skills, which are then needed to be combined in order to solve a particular task. So this is all like very fresh, and it's all very, very new. So the idea is, okay, we can actually have skills which we can interpret, like we need a skill X to understand parts of the sentiment of a sentence, and we need a skill Y to understand other parts of the sentiment of a sentence. So if we combine X and Y, we can actually understand the sentiment of a sentence, and maybe this skill X might be useful for some other task that needs to deal with the sentiment, et cetera, et cetera. So this is a very open research direction. So I will just quickly conclude that we have many unexplored variants on the multidimensional research manifold that we introduce here, which includes all these like computation, routing, aggregation functions, and even like training strategies, which we didn't even touch upon. And there is no one-size-fits-all design and model choice. So you have to actually take into account all these different things when you are deciding on your architecture. So yeah, how like computation parameters, storage budget, whether training speed is paramount, inference speed, whether you care about performance, or whether reducing the model size, reducing the training time, etc., etc. And I mean, this modular and parameter efficient deep learning actually transcends the confines of particular NLP thought. I think this slide is particularly important. So we could actually, I will put it after the final slide, which is, yeah, if you still have some questions, I don't know if we have time, feel free to ask us after the tutorial or send us an email, talk to Sebastian, who's in person. Hit us on Twitter, and watch out again for a survey paper on modular deep learning, which is deeply in preparation, and it was done in a very modular way with lots of people who contributed equally and in different parts of that survey. So I'll go back to this slide and I'll let it stay here. And sorry for overrunning. We just wanted to talk so much about all these things that we've learned preparing the tutorial. So thanks a lot.
Cool. Thanks so much, Ivan, and thanks everyone for sticking around. I think, yeah, if you want to go for lunch, you can go now, and I think if you want to stay, we can take a couple of questions. I think, if anyone has any. Cool. Yeah. Cool. Okay. Yeah. I don't see any questions right now. So yeah, we can. Let's thank Ivan again.
And also Sebastian and Jonas, of course.
Yeah, thanks everyone.
Yeah, thanks a lot for sticking around. And so again, sorry for overrunning, but
thanks. Yeah, and thanks for joining virtually and at the early time for you both. Yes, yeah, the slides are going to be the slides are available. Maybe one of you, Jonas and Ivan, you can paste the link again, just in the chat.